How are you?
Yes, ma'am. Fine, ma'am. How are you, ma'am?
Yeah, fine.
Thank you for
Going.
joining us once again, ma'am.
Yeah, thank you. Yeah. So,
Ma'am, there are totally 250 registrations for this course, and
okay,
daily almost 60-70 participants are regularly attending,
okay,
and they are joining exactly at 10:30 every day.
okay,
So
okay,
we will wait for 2 more minutes, then we can start the session, ma'am.
okay, fine. No problem.
Ma'am, I think we can start the session. Hello, ma'am.
Yes, yeah,
Okay,
okay.
ma'am.
Mm.
Good morning to you all. I welcome our today's speaker, Dr. Sumati from IIT Roorkee, with a brief introduction about her. Dr. Sumati is working as professor in the Department of Electrical Engineering, Indian Institute of Technology, Roorkee, Uttarakhand, India, where she has been since 2011. She served as visiting associate professor in the Department of Telecommunications and ICT, School of Engineering and Technology, AIT Bangkok, for the period of August 2018 to December 2018. Prior to this, she served as an assistant professor in the Department of Information and Communication Technology, Dhirubhai Ambani Institute of Information and Communication Technology, Gujarat, India, from November 2009 to August 2011. She received BE in Electrical and Electronics Engineering from SRM Engineering College, Chennai in 1996 and ME in Control and Instrumentation from College of Engineering, Guindy, Anna University, Chennai in 2002. She received her PhD in Electrical Engineering from Indian Institute of Technology, Madras, Chennai in 2009. She teaches undergraduate and postgraduate students for 15 years. She teaches the course on virtual instrumentation, advanced digital system design, signals and systems, digital signal processing, digital electronic circuits and systems, FPGA implementation of signal processing systems. She has developed a new course on FPGA implementation of signal processing systems and streamlined the digital electronic circuits and systems laboratory experiments with a pedagogical experience. Her research interests span over synchronization techniques, parameter estimation, sliding spectrum analysis, multi-component AM/FM decomposition, and instrumentation. Much of her work has been focused on developing sliding filter-based synchronization techniques for various applications and implementing them as system-on-chip devices with FPGA. These applications include ultrasonic rangefinder, vibration measurement, capacitance measurement, and flexible link manipulator control. In addition, she has also explored with the seismic signals attribute extraction through time frequency representation for damage detection of buildings. Presently, she is working on vision based advanced driver assistance systems. She has published 24 research articles in reputed journals such as IEEE and IET. She has also published 13 articles in international conferences. She has guided 3 PhDs and 21 master students. She is a senior member of IEEE and reviewer of IEEE transactions. She has completed projects funded by DST, DRDO, and BARC in control and signal processing algorithms. She has organized 2 courses on biomedical signal and image processing under MHRD scheme of Global Initiative of Academic Networks. She has delivered expert lecture on evolution of discrete Fourier transform in short-term course titled Innovative Techniques of Hybrid AC-DC Smart Grid Monitoring, Operation and Protection conducted at IIT Roorkee. Also, expert lecture delivered on evolution of sliding spectrum analysis and synchronization techniques in ICT seminar series conducted at AIT Bangkok. She has conducted sessions on power line systems, computer-aided design, and drafting PLS CAD software in professional development course on analysis and design of overhead transmission lines, PLS CAD AC 69765 kV operating conducted by AIT Extension Bangkok. With this, I once again welcome our speaker, Dr. Sumati, and now I may request you to start the session, please, ma'am.
Yeah, yeah. Thank you for the introduction.
Welcome, ma'am.
So very good morning to you all. I hope that you are benefiting through this course for the past 2-3 days. Okay. So my lecture, I asked them to be here because of the busy schedule that actually I asked her to schedule it in the morning of Sunday. Maybe if you have the provision, just yeah. Maybe the participants, maybe can I have some detail about the participants that are from
Ma'am,
colleges in
participants,
terms of
majority of participants are the faculty from different engineering colleges with the background of electrical, electronics, and instrumentation engineering, and almost rest of the participants are research scholars, ma'am.
okay, fine, fine. Okay,
They are
thank
above
you.
PG level, and some participants are at PG level.
Okay, fine. Okay,
Yes.
thank you, thank you. Yeah, I'll
Okay.
proceed. So just so all of you could see the screen. My
Yes,
screen.
ma'am. Yes,
Yeah.
ma'am.
Okay.
Yeah.
Okay. Okay. Thank you. So this talk, I have just named it "Interfacing Circuits for Capacitive Sensors." Capacitive sense is one of the area we have started working on recently. I thought I will share the content and also some existing techniques available for the capacitive sensors and the circuits which could be developed for the interfacing circuits. Okay. Anyway, the introduction is given by Dr. Satya, and also if you my email ID is this, you could always contact if you need anything. Okay. So I've just organized my talk with this contents, though the list seems exhaustive, but still will focus on the certain things like first to these capacitive sensors. I mean, many of you are aware of as an instrumentation engineer or an electrical engineer, we know that how the capacitive sensors work and what are the capacitive measurement technique we have, and especially the most of the techniques which are focuses on what is the sensible variables or sensor variables, and also how do we design these interfacing circuits. Some of the design circuits, how to convert this variable capacitance into some form which we can which is useful to us, or the physical variable, how to convert it into this interfacing, we will discuss in detail. I think, am I audible? Shall I go in this space?
Yes, ma'am, you're
Yeah,
audible.
yeah, yeah, yeah,
Perfectly
yeah.
fine.
Yes, yes, yes. Okay. So there are some direct interfacing circuits for RC with the microcontrollers, and which are very popular, and also some of the relaxation oscillator circuits even are designed with the here is the here some circuits are designed with the relaxation oscillator, and also for lossy capacitive sensor, the model of the lossy capacitive sensor we will discuss, and then how the digital readout of direct digital readout for the capacitive or impedance sensors, some of the authors proposed and are being used. Anyway, these two, the last two will not be our work, but still I want to discuss about this interdigital capacitors, or the interdigitated capacitors, might be you might be knowing, and then with conclusion and references I would like to wind up. So the introduction, everybody knows that's a very basic block diagram of a measurement system, or so you have some physical variables, and that physical variable is sensed by the sensor or transducer, and then you have some interfacing electronics, the interfacing we'll see what are these interfacing electronics, and also some signal conditioning or processing circuits, and then we use it for the display or the storage of transmission. So in this case, we have this sensor can be of humidity detection of humidity. This sensors, variety of sensors we know. Just I want to focus on this capacitive sensor instead of giving more detail about the sensors. I think we can go for the my talk will be focusing on these two blocks. Okay, so I'll give some details about the sensors even. And so they detect this can be for particles in oil, where detection, liquid level parameter, the liquid level measurement. This is known to us. Moisture measurement of the seeds and grains. That's a popular work which always to measure the moisture. They use the capacitive sensors. Let's see some of the details. So the capacitive parallel plate capacitor is known to us. It's very simple from the 10th or plus 2 physics. You must be learning this. These are the electrodes, R and S, and you have the dielectric medium in between. Usually this dielectric medium is denoted as D. So we are using some other variable for D. So I just named it T here. Okay, so the parallel plate capacitor has the can be expressed as epsilon naught into epsilon t by into A by T. T is that distance between these plates. Okay, so A is the cross sectional area. It's very well known, and so the capacitance can be varied with the cross sectional area, distance between the plates, and the relative permittivity. Okay, so this relative permittivity, so you want to measure the capacitance, then you can adapt three different methods. Either you can vary the cross sectional area, or the distance between the plates, or the relative permittivity of the dielectric medium. So these are the three possibilities you have to measure the capacitance or the sense the capacitance. Okay, so here the applications could be that I told you, measurement of displacement or moisture content of grain. So if you have the grain, the seeds, so So what is the moisture level of it? That is used in the agriculture field. That what is the moisture level of the grains? Okay, so that, for that also you can use the capacitance. Okay, so there are another type of capacitor. You can say three plate parallel plate capacitor. As we look at it in the sensor point of view. Okay, so this three plate capacitor has, you see, 1 2 3, there is a middle electrode T. So this 3 2 1 2 3, there is an extra one. So the middle electrode can be adjusted actually to get the variable capacitance. Okay, so the C1, so the middle electrode moves, one of the capacitances will increase and the other will decrease. So either it could be between the R and the middle plate, or the middle plate and the S. Okay, so the capacitance C1 and C2 can be adjusted because the T is specified here. The movement we can say it is del T. So T minus del T, one capacitance, and C2 another will be T plus del T. So the differential capacitance, the differential form of it, that is C1 minus C2, we can have always, this can be used for say differential capacitance. Okay, so the applications could be force measurement, pressure and angular displacement under the positions. Okay, so this is a one simple capacitor. So if the electrodes are fixed between these two, the one is the air medium, air electrode, the air dielectric, sorry. So here, then the three capacitive structure can be used for the measuring the permittivity even of the solid and liquid dielectrics. This particular capacitor can be used for that application. So C1 is a free space air capacitor, and C2 is the capacitor with the dielectric of epsilon R. The permittivity is to be measured, where the permittivity is to be measured. C1 and C2 permittivity is this, if you know this is C2 and C1, then you can measure the permittivity of the medium. So this is the way to measure the permittivity of the medium, how to use the capacitor, this particular capacitor for this. Okay, and you have even the fringing fields like in the interdigital capacitors sensors. I'll show you that the field lines will be from the you can show there are two parallel plates, and you can have the parallel plates in this shape, that the second figure. You can keep the material under test and in this gap. Okay, so the variation of the capacitance can be measured in this. So it's a parallel planar interdigital sensor, basically of two parallel plates. Okay, so one parallel plate can open up and you can put inside the material which you want to test, and then close it, so you can use it for the giving the excitation, and you can use it for the electric field lines I have just shown here might be known to you. And to this electric field lines generated by the sensor penetrate into the material, okay, which changes the impedance of the sensor. Okay, so that is how we measure the impedance. So the other category which you can say is the capacitive sensor. Okay, so this is interdigital sensor pattern. So you could have seen that comb structure. This comb structure, maybe this is very useful nowadays. This you can see this comb structure, and the capacitance, how the capacitance is measured. So the first, this is a positive plate here. The other, the types which I have discussed already, you must have known to them. This might be a different type of interdigital sensor pattern in which you have the positive electrode and here is a negative electrode. So each electrode is extended with the fringe length. Okay, so you have some length here. So we'll see one application using this interdigital sensor. Okay, so this is the length. So now how the capacitance is measured in this? Okay, so if you take one positive plate, this one comb length, fringe length, and another one is the negative electrode length. So the distance between this is C1. So that is, I mean, the capacitance between this is C1. This is acting as a dielectric for C11. Okay, so similarly with respect to first positive plate, and you have the second negative fringe. Okay, so this is C12. This is the capacitance here. In between these two, you have those are acting as the dielectric. So similarly, 1 and 3, we have the capacitance between this two, one and this is one positive. I'm just taking from the first fringe length of the positive electrode only, and then to the third one, there is a capacitance between these two plates, and also the first one and the fourth one. So it depends on the capacitance. It depends on the number of fringes you have, combs you have, and then you can always have the you can design this capacitor in your lab even. So this is C11, C12, C13 and C14. And next step is to take the second positive comb. With respect to this, what is the distance? With respect to this, what is the capacitance? With respect to this, what is the capacitance? So here, let's see. So yeah, this positive and negative, and this positive, the positive and the next negative is here. So next positive and negative is here. Okay. So there is a capacitance between these two plates. You can imagine that now. So there are M positive electrodes, 1, 2, 3, 4, 5 here, and then the capacitance can be Cm1, Cm2, Cm3, Cm4. N is represented for the negative plate. Okay, for 1, 2, 3, N is a negative electrode. So it depends on M and N. You can have the capacitance. Let us see how to calculate this capacitance values. Like equivalent capacitance can be C1, which is equal to the C11, C12 and C13. So here 1, 1, 1, 2, 1, 3, 1, 4 also, even you can add it for the C1 equivalent. Okay, C2 equivalent. Similarly, with respect to the second plate, with respect to the second positive plate, how many capacitances you have? 2, 1, 2, 2, 2, 3, 2N. So 3, 1 like that. So adding all of these capacitors, all equivalents. So with respect to the positive plate to the negative plate, all negative plate, one positive plate to the all negative electrodes, and second positive electrode to the all negative electrodes, and the third one to all negative electrodes. So this is the equivalent you have now. So the total capacitance is equal sum of the all equivalents. Okay, so that's how the capacitance of this is computed, the interdigital capacitor or interdigitated sensors. Okay, so the total capacitor depends on the capacitance value, depends on electrode's geometry, thickness of the electrode. Okay, so how much thickness we are using. So this geometry is, you can even change this geometry, like it is the comb shape. There are different shapes even. The distance between two electrodes and the number of electrodes of the sensor. Okay, so number of electrodes, how many you have, so depends on that. All of them can be the equivalent capacitance can be computed. So this is a fabrication of the interdigitated sensor. This is in our lab. We have just fabricated that for using it for some purpose. Okay, so this is one just a picture of it. I just show you with the interdigitated capacitor. So we use this for for the measurement of capacitance, the technique which we developed. So we want to validate the experiment. So just connect this capacitor. How much is the capacitor, which is the equivalent capacitor of this, can be connected to the circuit and measure it. Okay, so this can be used. We can put a water on it, so that in the electrode. So the change in capacitance can be observed. Okay, so that capacitance, the variation in capacitance. Suppose you want to observe the variation in this capacitance, you can put a water on the electrodes and the gap. Okay, so you can have that will have the change in capacitance or increase in capacitance value. Okay, so the water level measurement, soil water content measurement, especially this is used in the application of soil water. So water content cannot affect that water content always increases or decreases the capacitance. It depends on the water content. So it increases or decreases the capacitance value. So this is used in water level measurement and also soil water content. Moisture content of various agricultural commodities, like as I said, this grain, moisture content of wood pellets. So for this purpose it is used. This particular interdigital sensors are used. Okay, so these are these few known types of the capacitive sensors I have given you. So now let's take this the total technique of just an overview of this. So what? So is that clear up to this? Can I go ahead?
Yes, ma'am.
Yeah. Okay. Yes. Any response from audience? Audience? Okay. Yeah.
Participants, are you clear with
This-
up to
yeah,
this
yeah, yeah.
slide?
Okay, okay, maybe.
Okay.
Okay, no, it's okay. I'll proceed. It's okay.
Okay,
So
ma'am.
the thing is now this capacitance sensing so can be separated. I mean, can be categorized into different methods. It's like it can be a capacitance to frequency variation, or it can be capacitance to voltage conversion, capacitance to time conversion, capacitance, charge based capacitance measurement. So these are the different methods in which capacitance is sensed. So whether you want it a voltage or a time or a charge transfer method, so using these methods your interfacing circuit differs. Okay, so the interfacing circuits for capacitance is nothing but that the sensor which is actually present in the with the physical variable, connected with the physical variable, is available in the circuit. That circuit you want to the capacitance variable you want it to convert into voltage, time, or frequency in this forms. Okay, so especially we focus on this capacitance to frequency conversion. Actually, mainly the some of the techniques we have proposed for this interfacing. So one is this. Because the capacitance and if you take a relaxation oscillator, if you take in some of the circuits which I can tell you here, so conversion circuit. So these things in which that the capacitance and the frequency of this are inversely proportional. Our capacitance and this time are directly proportional. Okay, so when you take into the capacitance to time conversion. So what we thought is this capacitance to frequency conversion. We can use the some of the frequency estimation techniques also, and put them like instead of these interfacing circuits. Again, we can say we can have an analog circuit or we can have a digital circuits for getting this. Okay, from the capacitance value can be measured with as a voltage with the analog circuit or digital circuit or mixture, or some microcontroller can be interfaced in between to get the capacitance value. So so instead of going this for the digital technique only, it's for fully making it fully digital, a digital interfacing, or put it as a chip. These things can be done. So one is the frequency estimation technique. So if in the capacitance to frequency conversion, mainly the capacitance which is available in the circuit, that circuit produces a square wave. Uh, so if you measure the frequency of this square wave, you can always estimate the capacitance or get the capacitance out of it. Okay, so that's why. So if we have this square wave pattern, which where the circuit or the capacitance sensor is placed, so if we make that, if we compute that frequency, the particular frequency, then you are done with the capacitance measurement. So then we looked into what are the frequency estimation techniques or frequency measurement techniques that we can use it for this purpose. Okay, so it's good that if the capacitance can be just, if you have a high frequency pulse and keep sending using the clock pulse. If you measure the clock pulse, how many clock pulses you can accommodate in between the period, so you are done with the frequency measurement. That is very easy. Suppose the sensor circuit produces not a clean, it is not producing a clean square wave like this. So if it has a noisy one, and then you will have a problem at these edges, zero crossing points. So to detect how many pulses actually you have to pass it through, so in that it is very difficult to go about counting the number of pulses in that period. So what we have thought is that we in those cases we can use this some of the frequency estimation techniques to find out the capacitance value. Okay, so these are some of the frequency just categorized. I am not going to discuss all of them, just to give you the overview of it, and then we'll get into one or two one or two methods of it. So we have, so these estimation techniques, suppose how I this can be more or less okay. So some of the techniques which you use is a sine wave. Okay, so suppose you have a sine wave, you want to know the sine wave, this x of t, how much frequency, what is the frequency of this sine wave. Okay, So suppose I can say from the power line example that power line frequency, which you get it in the socket of your home, it is 230 volts, 50 hertz frequency. So that frequency, how do I know? How do I measure this 50 hertz frequency? Okay, so mostly for power line frequencies, and what is the that x of t? What you have is a sine omega t. So in which what is the f, 2 pi f, f, and what is the amplitude? And if you have any phase with any phase is attached are included in the sine wave. So if you want to measure that theta also, so those these cases, so to measure these parameters of the sine wave, okay, you can have the phase lock loop, or you can have the frequency lock loop, or you can have some of the parameter estimation technique especially to measure this. And there are some DFT structured FLL. So this is our focus area actually, which we work on mostly. So what are the DFT structure of our FLLs to measure this frequency? Here we thought the square wave also contains the harmonics, right? This fundamental second, third, fourth, all the harmonics. These harmonics can, if I make the square wave, change it into fundamental sine wave. I mean, filter out all the harmonics 1, 3, 5, 7, all of them, all the harmonics from this. Then I am left with only the fundamental sine wave. So if I know the frequency of the fundamental sine wave using these methods, so then I can also estimate the capacitance. That's what the idea. So fundamental sine wave, that's why we have chosen the online sinusoidal frequency estimation techniques, in which so your circuit where the capacitance is placed. For example, a relaxation oscillator. I'll give you the circuit anyway. So that circuit produces this square wave. Sorry, this square wave, I filter it out for only the sine wave. Take out only the sine wave from this square wave. Again, square wave to sine wave conversion is required, and then I measure the frequency of that. Okay, so then it is very. So these methods are based on that. Maybe that SOGI, that is second order generalized integrator. So that is a method which uses the a structure, that is a filter structure, which you can use it for quadrature signal generators, and then sliding DFT, modulated sliding DFT. These phase locks of loops are designed based on this filtering to estimate the frequency, amplitude, and phase, like that. So, and then moving average filter, modulation function with second order generalized integrator. Okay, so there are FLS, frequency lock loop. Maybe the difference I can tell you what is that phase lock and frequency lock. Multi-resonance SOGI, second order generalized integrator. You can have a couple of second order generalized integrators in parallel in the FLL structure to measure these frequencies, corresponding measure frequencies. That means if the capacitance variation is large, then you have to cover the entire range of capacitance. That means what is the instrument which we use it for measuring the capacitance is that LCR meter, right? So in your labs, maybe you have the LCR meters. So inductance, capacitance, resistance. So have you heard of anybody?
Yes, ma'am, we have heard of.
Yeah, LCR meters. So in that LCR meter, you have seen that it is covering a wide range of capacitance which you could measure, right? So even the you can have the 10 power 18 farad, the good LCR meter, maximum it can measure 10 power 18 farads. So at the minimum of even you can have the picofarads, nanofarads. So the range of this is the maximum, I'm saying. So in that case, you need to cover, if you use this frequency technique, you need to have the wide range of measurement technique. So you can have these frequencies can be of very structured with this second order generalized integrators to cover the maximum range of capacitance. And this is all digital FLL. I will also give you the details. And you have the moving window DFT based FLLs, and then third order generalized integrator, fourth order generalized integrator, nonlinear adaptive estimators in the case of parameter estimation technique. These are traditional techniques actually. This third column, which is giving global convergence, and then adaptive that is notch filter, adaptive notch filter, and then algebraic identification method. So these are the traditional parameter estimation methods for finding out the frequencies of the this sine wave, simply sine wave with noise, corrupted with noise even. So here STFT I have shown you, that is sliding DFT, modulated sliding, hopping, modulated hopping DFT, and then a Swift invariant Fourier transform. These are not. I'm not going to discuss everything in this, but I'm just giving you the overview that this can be done like this. The capacitance sensing can be done in this way. That's a novelty that we bring in our work. Huh? Okay, so just a simple capacitance to time conversion. So how the capacitance is converted into time. So that if I know the time, then I know the capacitance variable, and the variable which changes, a physical variable which changes the capacitance can be identified. Either it could be a moisture, or it could be yeah, that's it's the applications, like what are the capacitance change applications, like displacement, all those things. Okay, so here is in the structure you can see that feeding one circuit to the other. There is a comparator and a differentiator or integrator. Okay, so the comparator, these are op-amp based circuits. I am just discussing the op-amp based circuits. These are analog circuits. Okay, so not digital. So the one which I was talking about in this slide was fully digital. Okay, that means you can have it, you can program it in the DSP or the FPGA and put it in that. So only you need to have the sensor circuit and then feed it to the chip, and it will give you the capacitance value. So here is the analog circuit. So you have the comparator. You can just look at this picture. So I have given these two figures here. One is for the both are having the comparator. Here is a comparator in this circuit, and here is a comparator in this circuit. And with the comparator output, it goes into the differentiator. So here is the differentiator circuit, the first one. Okay, and this is the integrator circuit. Okay, so you can have the comparator with the integrator circuit also. Okay, so if you have here is suppose it first we'll take this first circuit. So you have the comparator. Suppose that the output V out is this is a square wave actually. Where is the capacitor which you want to sense is this CS, the capacitive sensor. Similarly, the capacitive sensor in this circuit is this. Okay, so now if you vary the capacitance, so the differentiator circuit always changes this. So what would be the differentiated output? You will have this pulses, right? So this pulse is compared with the voltage what you have at the input. This is going here, and when it is exceeds that, it is going it is sustained for next pulse, and then up to sustained for the next pulse, and so on. So you get the square wave. So this square wave is totally depending on the capacitance. The frequency of the square wave is depending on the capacitance which you change. So what is the charging period and the discharging period of this? So here, so your capacitance varies this time period of the particular output. So similarly, if we have the integrator, so the integrator, this output is a square wave. So here integrator output will be, we don't have the picture, but okay, so you can have the integrator output. This is fed here. So it is going to be a triangular wave here. Triangular wave. So the triangular wave is compared with a certain this voltage 0. So whenever it exceeds, it goes to the VCC plus VCC, and whenever it comes down, it is going to the minus VCC. So that's why you get the square wave. I think this plus VCC and minus VCC are the maximum supply voltages which a comparator can when op-amp can produce, right? So that is the voltage. So which you have then get. So from here the capacitance. So depends on this integration time. The period is decided by this RC, R and C. This RC. So the charging time and the discharging time, and then so this charges through the R for a certain time, and then discharges. I don't have the diagram for this, but I just give you this. So this will be a triangular wave, and then here is the triangular wave which is compared with 0 in this comparator and getting the square wave. So here what we did is this capacitive sensor, we changed into the time, that this particular square wave variation, or you can say it is the frequency also. Okay, so here is also the capacitance change could be converted into the time. So this is the circuit for the capacitance to time conversion. Okay, so now if I converted the time, so how do I measure this time? Okay, so I feed it through a one clock pulse of the microcontroller or the DSP or FPGA. So you can pass this clock pulse for this particular period. Okay, so you can start counting, or you can have a counter with this counter, which is having see, the counter starts counting at this point whenever this square wave starts. Okay, so you keep counting, and you stop the counter at this age when the time period gets over. Okay, so then you find the how many count pulses you have counted for this particular wave. Okay, so suppose I have the 50 counts, and 50 counts, and this clock pulse variation, suppose it is 50 megahertz clock. Okay, so you can always find this time. So 50 counts, I have one clock pulse duration is 50 megahertz frequency. Okay, so 1 by 50 megahertz into this number of counts. So you would get the time period of this particular wave, so which is proportional to the capacitance. Okay, so this is a simple circuit which can give. So but people use this further. So how do you need to have an hardware for this counter, and then the clock pulse and all those things, so that microcontroller or the DSP plays into a role. So you have to program the microcontroller or the DSP for this particular take. You have to take this waveform through the ADC to the device, that is the DSP or the microcontroller, and then there you can keep counting, do this, and then and goes to the display or the storage. So capacitance to frequency, again here is the circuit the similar way, but that there is a small difference. We can say, why do we call this capacitance to frequency and capacitance to time even. So here is the oscillator circuit. So that the oscillator circuit is this. So it's if you, I think most of you know that it's a relaxation oscillator. How the relaxation oscillator works. So first you have some V naught. This is V naught. Suppose assuming that V naught is at plus VCC. Okay, so it depends on VCC what you give. So what would be the voltage VP here? VP is VCC into plus VCC. I am assuming initially it is at plus VCC. VPP VC R1 by R1 plus R2. Okay, this particular voltage is applied here. Okay, so suppose Vn is the voltage, whatever the voltage at Vn, this Vn exceeds this. Okay, so if Vn, let's see which, then at this after coming here Vp, so Vn is greater or Vp is greater, that is decided by the op amp. So if Vn is greater, then your plus VCC just snaps it off to the minus VCC. The output will go to the minus VCC. Okay, so or your VP is greater than Vn, then output will be at the VCC only. So VCC only, and then it goes, the capacitor gets charged. Okay, at this time, okay, it's charging the capacitor through this resistor. Okay, so this will be keep on happening. So once it is charging, this voltage gets changed, so your VP gets changed, so it will be shuttling between VCC and minus VCC. The output will be shuttling between plus VCC and minus VCC. Mostly we use this 741, which is having the if you give the plus VCC and minus VCC of 15 volts, and you will have always the in practical op amps you will have the reduction of 2 volts. So that is plus or minus 13 volts you can have at this point, plus or minus 13 volts. Okay, practically speaking, full voltage if you apply, so that will be oscillating between this square wave. This square wave will be oscillating between plus 13 to minus 13. Okay, so you can fix the external values R1 and R2, and whatever the threshold value you require, how much should be this VP, and so then this the capacitance sensor, so which affects the When it is charging, it will be charging at one point and then it will be discharging, charging and discharging. You can get this waveform here, even in this charging and discharging waveform at this point. Okay, so so if I know the period or time period or the frequency of this, I can always measure this capacitance. So for measuring this only, so that's what this is, the oscillator circuit, and the capacitive sensor is always connected to it. So you find your capacitive sensor with some op amp analog circuit, and then the excitation supply is mentioned, this plus VCC and minus VCC. This generates this resonant frequency, which is depends on the capacitance. And then if capacitance changes, there is a resonance frequency shift occurs. So that's what we mentioned as del of frequency shift change. Either this time period will be contracted or it will be expanded, depends on the capacitance value. So if you have capacitance and this frequency are inversely proportional, if you have more capacitance, the frequency will be less, and then if you have less capacitance, you will have the frequency will be large. So estimating that frequency, okay. So is the challenge. Again, I told you that that frequency estimation techniques, or there are many techniques, you can always use it. Okay. So in this measurement system, that is that hope are you able to follow? Otherwise, it has no meaning that if I keep on talking. Yeah.
No, ma'am. It's understood. Yes, ma'am.
Yeah.
Yes,
Yes, we
ma'am.
can.
Yeah.
Yes,
Okay.
ma'am. It's understood.
Okay. Yeah. Okay. So now the capacitance measurement system. Now the whole measurement system, what are the things you may have? That is what. Here is the circuit, that oscillator, a simple circuit which I told you, and the capacitive sensor is given, and the oscillator, and some of the square wave. I told you to use the online the frequency estimators. This for finding the frequency of it. What you have to do, you have to filter out this square wave to sine wave. Okay, so some of the techniques, sinusoidal estimation techniques, works only for sine waves, which are the square waves which are converted into sine waves, and these sine waves are fed to this estimators so that it can give the estimated frequency, and then that estimated frequency corresponding to which capacitance it can be calibrated in this. Thus you get the measured capacitance. But some of the so this conversion is required in some of the sinusoidal estimation techniques. So maybe we can name those techniques which require this. Actually, filtering is required. But some of the techniques, sinusoidal frequency estimation technique we have, that can ideally work for even you don't need to convert it into sine wave. You can just directly feed it to this estimation technique. So this takes the square wave itself and computing the fundamental frequency. Okay, so maybe I advise, if you are interested, you may read our article. One of the article, I'll give you the reference that you can read it further. For any of, if you want any of this, you can refer that paper. So the RC which I was talking about, the frequency here, this is one RC, R1 R2 is this ln of this is the relation of frequency, and so here you have the capacitance inverse relation. So this technique can be PLL. Okay, so here you have an oscillator, sine wave. This sine wave whose frequency is to be measured is given here, and you that is in the this is called the phase locking scheme or phase lock loops. So similarly, frequency lock loops can also be designed. So here phase lock loops, this voltage control oscillator it's a built-in oscillator which has a certain frequency, suppose F0. So your frequency here is coming to be F1. So this multiplier K, this is a phase detector. This is a phase detector. So F1 and F0, these are I am not literally, I am not, these two are multiplied here. So F1, F0 means the corresponding sine waves. Sine 2 pi F0 t plus, and then sine 2 pi F1 t. So okay, if you multiply these two, you will have. So suppose this frequency is omega 1 and this is omega 0. You will have in the multiplied output, you will have omega 1 plus omega 0 and omega 1 minus omega 0. If you cross multiplied, one will be DC, another will be to second harmonic will be available here. So to filter out that second harmonic, this is given, that is low pass filter. So it will pass only the DC component, omega 1 minus omega naught, the variation in this, the variation between the incoming frequency and the controlled oscillator frequency. So the variation between, or the difference between these two is only passed here. And this voltage control oscillator will adjust to the will try to track this omega 1. So try to produce this frequency which is close to the F1. So this action will continue until this omega 1 and omega naught will be equal. Okay, so that is what the lock is. So once it is locked, once the error becomes 0, so it starts giving the so this will give you this output will give you, this oscillator output will be same as the this input. So we will know what is the frequency which is incoming and what is the amplitude of the signal and what is the phase of the signal. Everything can be found from by tapping out this particular output. Okay, so this is for the phase lock loop. So similarly, the frequency lock loop, which is like, instead of a phase multiplying and finding the phase between this this adjustment, the error is used, the phase error is used. Whereas in the frequency lock loop, the frequency error is used for this adjustment. So where the is actually speaking omega 1 omega naught into t. Okay, that is a phase. In the phase lock loop, the phase information is used, whereas in the frequency lock loop, the difference between the frequency error is used for this correction. That's the difference. And always we know that omega t equal to theta. In that case, if we want omega, it is going to be d theta by dt. So if theta is suppose step, then its differentiation will be an impulse. D theta by dt will be an impulse. So omega will be impulse in that case. Okay, so if your phase is the input change phase is going to be a step change, then the frequency change will be an impulse change. Okay, so that's how the relations of frequency and the theta are decided, whether step change in phase is possible or not, whether ramp change in phase is possible or not. Okay, so for all these things, phase lock loop is fine, but frequency lock loop, this is impulse change in frequency, we will not, I mean, it is very difficult to identify. So so that's what step change in frequency, okay, it will find out that. Okay, so that's where the difference between phase lock and frequency lock loops are there. So that is fitting in this capacitance measurement system here. Okay, online frequency estimator. Once you know this frequency of this, then that is equivalent here, conversion of the relation between capacitance and frequency is computed. Okay, so sometimes if you see in the circuit the capacitance you have and the square wave is produced, so that is obeying 2 RC ln 1 plus, actually this is a formula which you, if you simplify this, I mean, if you take out the mathematics equations from it, you can get that. But the capacitance and if you physically construct this circuit or assemble this, but you may not get the ideal frequency which you are calculating for a particular capacitance. Okay, so there is a deviation in the practical circuit that is due to the op-amp property, either the slew rate, bandwidth, unity gain bandwidth product. So these parameters affects that difference in capacitance or the frequency which we are computing here. Okay, so the problem is the capacitance sensor and the frequency output of the square wave frequency are inversely proportional. If you calculate it through a formula, you get one value for this particular frequency, but actually construct the circuit and connect your capacitor and find out the frequency of it, but you may not, there must be some variation, theoretical and the practical cases. So that is due to the op-amp non-idealities, you can say. So those things and all doesn't matter in this digital part. Okay, so digital algorithm, what it will do, just it takes the square wave and whatever the frequency you are giving, it will estimate properly. So the error which comes out here is independent of the op-amp errors. Okay, so op-amp errors we have to compensate here only in the analog part only. So the variation which you are getting in the frequency, that has to be compensated by making it closer to the making this frequency closer to the ideal frequency. That is possible by using some capacitor compensation circuit. Okay, so that can be compensation circuit can be here if you connect a resistor. So maybe if you do the full nodal equation and all, so you can see the difference between that change in the capacitance and the compensation. So that is those are compensation techniques which are used in the relaxation oscillator. That is another different area. So I'm just giving you this overview of the measurement technique using the relaxation oscillator, in which the digital part is the interfacing circuits. Okay. So there are fully this capacitance to frequency conversion we are looking into. This capacitance to frequency conversion, there are all digital FL. So the FLL is fully digital. Frequency lock loop is digital. Okay, so the same frequency lock loop will also contain these things. The phase detector or the frequency detector. One component will be frequency detector, low pass filter, and then voltage control oscillator. Okay, so this is fully digital. Means this particular one, you can refer this paper if you want. So this particular FLL is implemented in a FPGA for capacitance measurement only. So there is a crystal oscillator, because in the FPGA's field programmable gate arrays, you have the clock frequency. That chip board, FPGA board will have a clock frequency. Mostly it will be 50 megahertz or 40 megahertz clock, depends on the FPGA which you use here. So that is divided into some, because high frequency clock is divided here. The input square wave. Okay, so this is going to be the square wave which is coming from this relaxation oscillator, this one or any of the above circuit. Okay, so that frequency has to be computed. Actually, this is computed as n. Okay, so the input number of pulses between the period is computed here. Okay, so now how this is done? The clock, there is a synchronous counter. This starts counting when the clock pulse comes. It starts counting. Okay, so when to reset that counter, that means counter, you may know that it will start counting like this, keep on counting with one every clock pulse which is coming in. Okay, so if you have 1 2 3 4, so it will go up 3 4 like that. When to reset this counter? Okay, so that operation is done here through this. Okay, that is, it is decided by the sync counter divided by 2. So it is taking the sync divided by 2, which is going here. There is a comparator, frequency comparator. The input comes in and the comparator compares what is the frequency here, and that is what this is acting as a phase detector or frequency detector in this way, in this FLL. Okay, so then it is less, so count up, or if it is more, it is count down. Okay, so it adjusts the synchronous counter, up and down counter. These counters are, you can refer this paper, but these counters are made with flip flops. You know, the digital logic design. You just recall that we use the flip flops for designing the counters. So these are literally flip flops with that counters. So it will give n according to the frequency, whatever the frequency. So one SN is achieved, this logical comparator will stop this. So okay, the decided counter value is reached, so stop it. Okay, so that is how this operation is going on. Done. So the frequency, the input square wave frequency is now converted into n number of pulses. So suppose you have the 50 hertz, it may be showing 50 pulses if we have 1 second pulse, or it is 50 megahertz pulse, depends on the frequency of this pulse. So it will show the n. It is directly proportional. Okay, directly proportional. So capacitance to frequency version of this is all digital. That means every component is digital. So logical operation and fully implemented in FPGA. You may refer this particular paper for by these authors. The capacitance to frequency conversion. This one. This is all digital FLL. And there are capacitance to frequency conversion, again this SOGA based FLL, I mean that frequency lock loop. So maybe I'll just give a little bit of this information and then move on to the next one. So here is the capacitance to frequency conversion. SOGA is this at a second order generalized integrator. Okay, so second order generalized integrator. What is the big thing about this second order generalized integrator? So you can have these two integrators. This structure, the one which is shown, I think the dotted lines. These dotted lines are the second order generalized integrator. Okay, so this SOGI, and here is the FLL, frequency lock loop. So second order generalized integrator is it's again it's a filter. We can design it in the software. Okay, so it is not, it doesn't require any of the hardware. It doesn't require, this is not an analog thing. So it's a software, so you can implement it in the DSP, or in the case of you can even implement in the FPGAs. This SOGI, you have two integrators. That's why it is the second order integrator. So what are the input you give here? This SOGI, what it will do actually? Input here. So it will give the sine wave. Suppose you give a sine wave of frequency f. Okay. So this would produce a in phase and quadrature component. So in phase component is it in the sub when it is tuned to a particular frequency omega. Okay, so that is what omega. So if you give a sin omega t, this will give a sin omega t and a cos omega t. Okay, so in phase and quadrature components can be generated using this. This again is a quadrature generator. The thing is, see here, this is here you get in phase component, and here you get the quadrature component. This is the quadrature component, and this is the in phase component which you get V dash and Q V dash. So now see, the in phase component is taken here, and the input your square wave from the sensor circuit comes here, square wave. Okay, so the square wave and the feedback which is going to be a in phase, that only fundamental sine wave. This will be a fundamental sine wave. Okay, so are subtracted, and you get the error between this. So this error is processed. You can see this error is processed. This error and the output from the quadrature component to this is giving the frequency error actually. So this frequency error is integrated to get the omega. So this frequency error is integrated to get omega, and that omega is adjusted given in this equation. It has some equations also. I am not giving that details. So W dash. Okay, so initially suppose this frequency is omega 1. Initially this frequency is omega n. So this frequency is omega naught, nominal frequency. Okay, so this would produce omega naught only. Okay, so this produces omega naught. This omega naught sine omega t goes here. Subtraction gives the error. The error and the due to omega naught, what quadrature component is produced, get the error between these two. Okay, and changing this omega naught to follow omega 1. Okay, so just little bit, every adjustment will be to moving towards this omega 1. So omega naught will be just adjusted to follow omega 1, so that this will produce whatever the sine wave frequency of omega 1. So this operation continues until this error becomes 0. So that is what the logic, the operation behind this, the second order generalized integrator. So this can be used as a quadrature integrator also. So this particular technique can be is used in the capacitance measurement with the square wave. Okay, so if once it is tracking, you get the frequency over here. Once it is tracking, you get the frequency over this place. Frequency here, frequency you can get. If you want the amplitude of that particular signal, you can always get it from the sine your a sine omega t will get here, and a cos omega t will get here. So from V dash and Q V dash, so square it and take a root, so you get the amplitude of this too. So you can get this from this. This is because it is processing the frequency error. This is called a frequency lock loop, not a phase lock loop. That's what FLL is. So this is anyway our the technique that which we have produced. Maybe I can discuss about this some details, and then we'll go to the some traditional techniques also. So this is our relaxation oscillator that I have told you. So why we have what we are going to do with this actually? This relaxation oscillator, if you could closely observe, there is one resistor and there is another capacitance. So you can use a simple same relaxation oscillator. That's what the idea we have framed, that the relaxation oscillator only I told you the relaxation oscillator how does it work. Okay, so you get a square wave here, depends on the capacitance value, the frequency changes. Okay, so the two variables, so you can either measure this variation can be obtained if you closely look at the formula which I gave, 1 by RC. So those are inversely proportional, R and C, the R and C. So the frequency variation of the square wave can be due to C, or it can be due to R also. So either you can use it for capacitance variation, or capacitance measurement, like the moisture measurement, or you can also use for temperature measurement, the same circuit. So this is resistance variation. So we connected a RTD and change this. Okay, so change the resistance of this. So depends on the temperature. Put it in a, just for testing, put it in a water bath, that RTD, and that connect the RTD here, so that it gives the changes in the square wave frequency variation. So that we can measure the temperature, and we can also use it for moisture content measurement, the same circuit. So this is the idea. So after producing the square wave, that what we are talking about, it is literally going to the FLL part, which I have given in the previous slides. So here is the DFT, recursive DFT. This is our technique. Maybe a little bit explanation may be required. Recursive DFT is that, maybe I don't know how many of you familiar, but then let's just give the small brief idea about that, so that this will be understood. So as I told in the SOGIs, so our STFT or RDFT, recursive DFT, can also give the in phase and quadrature component. The same in phase, this is quadrature. So in phase and quadrature component, for when give the input maybe a square wave, or it could be a sine wave, and it needs an extra thing is like a sampling frequency Fs. Okay, so this adjustment we do usually in this case. So input is passed. The input can be a square wave or is a sine wave, I told you. So it is this, if you measure the, suppose the F equal to K into Fs by N. Suppose you want a sinusoidal of frequency F, and that is a fundamental K is indicating the bin index, that is fundamental 0 or 1, 2, 3, and Fs is the sampling frequency, N is the number of samples in a particular sampling cycle. Okay, so this is N. So N and the number of samples in it are N. This is Fs is the sampling frequency, you know how much distance we allow between the sample, and this F is the frequency. So if I give, suppose this F I want here, so I need to F into N should be my Fs. Fs should be I properly supplied to the structure, so then it can give the in phase properly and quadrature properly, even if you give the square wave. Okay, so that means it will filter out the remaining harmonics, and it can give only the fundamental. So that's the idea. So here is a square wave, which is going to give the square wave to sine wave conversion is happening here. Okay, so after getting this in phase, is passed on. Why all these things are required? Because if this can change, this frequency can be changed, because due to the capacitance or resistance, the square wave frequency will be changed. So this sign is passed, and then the error is computed like the previous structure, and it is passed to the, like an SOGI, it is again the recursive DFT, and the in phase component is taken for error, and our quadrature component I have taken it for sampling pulse adjustment, because when this frequency changes, the input frequency changes, I need to change the fs also here. Okay, so f is also changed because f into, if f is changing, n I am keeping it constant, f into n, if 50 hertz to 45 hertz or 55 hertz and n is constant, so this fs will change. So fs has to be changed. So that pulse is changed and given here. This is fs mechanism. So here also fs. This is done through certain procedure like finding the error and changing the sampling frequency. This is sampling frequency adjustment. So once these two blocks are getting correct sampling frequency, what f I need, what is the input frequency I am giving, corresponding fs is given to the FD, it gives a proper sine wave and the error becomes 0, and it gives the quadrature component, this gives the in phase component. Okay, sampling frequency is adjusted. Okay, so this particular block may not be required. This may not be required if this is not changing in the center frequency of this would be changing, because if due to our measurement this frequency will be changing either by R or C, it will change. So our frequency, the estimated frequency, where am I getting this frequency, estimated frequency, this f, so here is a block inside, f estimated can be found from this block inside. So this f estimated is the indication of the capacitance. So what would be the inverse relation will be followed between the capacitance and the estimated frequency. Okay, so this is one circuit. You have only the analog part is only this much, only analog part is this much. Okay, so analog circuit is this, the remaining are digital. So the remaining you can code it in the digital. So maybe you can see this, that what we have done in the lab. So FPGA board, that is, and the ADCs. So because we need this signal, the square wave has to be fed to the board. So we need the ADC here, ADC. And to observe the signals at various points, we have used the DAC also. So this is ADC and DAC, and the simple structure, this relaxation oscillator is here, relaxation oscillator, and we have connected the RTD with the water bath, showing that some temperature, and this RTD is connected to the circuit, and we could see this output of in phase and quadrature component and the square wave, which is merged. Maybe if I zoom it, you can see this square wave and the sine and in phase and quadrature components. Okay, so this is the program which we made in this. Okay, so actually we use this. If you are interested, maybe you can see that FPGA DSP builder. Builder software with the MATLAB Simulink interface for doing these operations. Okay. So this is about, now I have discussed about the capacitance to frequency conversion, especially how we can do and what is the small interfacing circuit used. So generally this interfacing circuit now is been, this is same, that sensor you will have, and you have the excitation signal, anyway excitation signal, that supply voltage has to be given to sensor and signal conditioning unit also. So you'll get voltage or current. I told you about the voltage or current time or the frequency, we were discussing about that. So this signal conditioning block performs output to voltage conversion, amplification, filtering or linearization, demodulation. Some certain things are recorded in this signal conditioning circuit. Okay, so anyway, in the previous circuit which I have shown, just I have taken the square wave. So there is nothing, no other analog circuit interface to that. But here maybe some of the circuits we have in which you can have the you have to have your signal conditioning circuit. So one such maybe the other one is like sensor and microcontroller connected. So you can have the excitation signal to the sensor is given by the microcontroller, and the output from this quasi digital signal or from the sensor, microcontroller takes it and for processing. Okay, so this is a direct interface, sensor and microcontroller interface. So in between there is, you have a sensor and you are not having any analog circuit in between, just a microcontroller chip, and in one of the pins you connect the sensor. Okay, we'll see that also, how to do that. Block diagram of a analog circuit with microcontroller. So sensor and there are some signal conditioning circuit and the ADC, and then it is going to the microcontroller. Okay, it is not directly connecting to the microcontroller. Okay, so it is not like the previous case. It is going through some process of signal conditioning and then the analog to digital converter and then to the microcontroller. So this is sensor analog circuit with microcontroller. Okay, so there are direct interfaces where you don't need any analog counterpart. Okay, so in this case you need some analog counterpart. So there are these direct interfaces can be two types. Okay, so the microcontroller block performs the following operation, like it acquires, it stores the signal, processes, controls, and communication to the if suppose microcontroller output is desired, so the capacitance value which you measured may be given to some other displays a digital value. So it does all this operation, the microcontroller. So these direct interface circuits, this one, what we are talking about, the first one is based on RC circuit. Actually, you will have RNC component. I'll show you that. Music that measures the time interval needed to, if microcontroller is connected to a RC circuit, always charging and discharging happens. So it needed to charge and discharge a capacitor C, okay, to a given threshold voltage through resistors R. Okay, so this method has been applied to measure resistive and capacitance value of the sensors. So if we have a sensor, capacitive sensor which has the lossy capacitance, lossy capacitance model, in that you will always have a resistor. So maybe I can show you the lossy capacitor model first. Yeah, this is the lossy capacitor model. Actually, if you have a capacitor sensor, the capacitor sensor, maybe I'll cover this. The circuit based on this quadrature in phase and the component and the quadrature component. So you have a sensor in this capacitance sensor. If you consider that is to be lossy, then you will have a resistor in parallel with that, and also a parasitic capacitance on the two nodes. Okay, so the floating type capacitive sensor node 1 and 2 are available for measurement. This 1 and 2 will use for measurement. So this, in this case, that in the ground type capacitive sensor, one is always grounded that way. So lossy capacitor model is, you can imagine that this is what is. So it's not only CS, it will have RS in parallel, especially though you avoid the parasitic capacitances, but the parasitic capacitance may be avoided, but still the lossy capacitor model will have this parallel resistors in parallel resistor. Okay, so we'll discuss this model next maybe. So I'll go to this again and come back here. So this one RNC. Suppose you want to measure that RNC, which I have shown in that case. This is what CS and RS. Suppose we want to measure this. So then this particular microcontroller and this model, how we can use it for the interfacing. It's a direct interface. So direct interface based on charge transfer, where microcontroller counts the number of charge transfer cycles needed to charge a reference capacitor to a given threshold. This via capacitive sensor. It is applied to only capacitive sensor. Let's see that how this method works. Simple RC circuit, how does it get charged? So if you give your voltage V, VI, V1, so it gets charged. Okay. So after full charge, see, this is what the charging cycle shows. So you have a V1 giving V1. So this is the voltage V1 given at this input. The voltage V0, you can observe that this is charging over a time. Okay, so we fix a threshold VTH. Okay, so that is decided anyway. We'll see that VTH. So if the voltage V0 exceeds, so this voltage V0 when it exceeds VTH. So you stop here. That means that is a cycle for charging process. So from T, the moment which you apply at VI to the charging, when it crosses the threshold voltage. So that is the charging process. Okay. So and then we'll take this measurement. So you can start a timer for when the input is given, and then you stop the timer when it is reaching VTH. Okay, so that is timer is inside the microcontroller. Okay, so here the other one, if you give, this is a up pulse, that is step up pulse, and another one is a step down pulse. If you give the step down pulse, then say next is given is a step down pulse in the VN. Okay, so the charged capacitor is allowed to discharge. Okay, so it is the charged capacitor now, it is allowed to discharge. It will be through the output here given, or through a path will be provided for this capacitor to discharge. Okay, so if it is so the moment the down pulse is applied, a microcontroller timer is start. Okay, and there is a lower threshold, VTL is fixed. So when the discharging output V naught crosses this, you stop the timer again. So this is the delay or the discharging process. Okay, so you have the charging process time and the discharging process time. Okay, you don't know the value of C, that's the capacitance value, that's a capacitive sensor. Okay, so how do we calculate this? TC and TD are calculated by giving the known voltage Vi. So C is initially discharged, and step of amplitude V1 is applied, so that you get V naught equal to 1 minus, because it is going to charge, so V1 to 1 minus e power minus t by RC, and the time required for C to go 0, that is to TH. This is the charging period from 0 to this. So this is TC equal to RC ln V1 by V1 minus TH. You get this from here, this computing this as a TC, putting it as a, so you will get this equation. Okay, so TC is known. Okay, and then similarly we apply the step down pulse towards ground, so that is going to be decaying exponential. So V1 e power minus t by RC. So from this t is substituted as TD, so V naught is going to be VTL, so V1 by VTL you will get, so RC VL. So TC and TD are known. So from the TC and TD we can measure this the capacitance value. What is this? What is the value? The time. So here, where is it? It's given. So if you know this TC and TD, we can measure it. Let us see how to use that TC and TD in these cases. Okay, with the microcontroller. So the direct interface circuit with a capacitive sensor. So this is a capacitive sensor. Okay, so connected to pin P, and this is pin 1, and there is a known resistance RD is connected here. Okay, so first this is a charging process, in which what we do is this pin 1 is given 1 means the supply voltage. Okay, so supply voltage 1, this pin is made as 1, giving the supply voltage 1, and for this pin P it is made as the supply voltage 0. Okay, so then that time this is known. So what it will do, this is at the higher potential now. Okay, so this capacitor will get charged. So this capacitor gets charged because this is at the ground potential. So it will get charged in the process. RD is known. The charging time, you can say, is noted. Charging time, and then so we can say this TX time. I'll come to this. So when you make this sensor 0, P2 pin 2 0. No, pin 2 is the next one. So see, this is charging process, you understand. And then here similarly, when we make this keep this 0, pin P 0 as such. So during the discharging process, make this 1, this pin 1 high impedance. Actually it is a floating point, there is no connection to this CX. Okay, so it made as floating point, so it will start discharging through RD node. So if you know the charging and discharging time of RD known, RC time constant is known. Okay, so then you can always find out the capacitance value. Okay, R is known, and so capacitance value can be found from this. So this is, we don't even connect any of the other analog capacitor, only with the microcontroller and the sensor, and one resistor R and C we will use for this particular to find out the capacitance values. Okay, so this is another direct interface configurations. So you can have the CX is the sensor capacitance. Okay, and C reference, you have the reference capacitance, and RD is known capacitance. RI is in known resistance. Another resistance RI is connected to just RI and CS, or this CS. And for the power supply, some noise rejections, it is introduced to the circuit. But the CX can connect it to pin 1, and similarly pin 2 is here with the lossy capacitor model. Okay, so this is for lossy capacitor model, and you can see even in this it is a differential capacitor model between 2 and 3. Okay, so the same thing, 2 and 3, and here is a bridge circuit model. Okay, so there are only the microcontroller and the capacitance of different types. So we have the simple capacitor, lossy, and then differential capacitance, and then the one which have with the bridges. Okay, so this can be found by so that first three things are observed here. One is the sensor time, sensor with the sensor, what is the time, reference with sensor capacitance, I mean, with what is the time, discharging time. Okay, so reference, what is with the reference capacitor, what is the discharging time. Okay, and then with the offset, both pin 2 and pin 3 making offset, you get some time. So from this there's a formula here, we can always compute Cx can be computed by Tx, knowing this times, discharge times, difference sensor discharging time, and then the reference capacitor discharging time, and the offset means you will have this pin 2 and 3, both of them are is at pin 2 and 3. In all these cases, pin 2 and 3 are made in this case pin 2 and 3 are made high impedance, floating. So then what is the time? So T of time is noted. So these time are used for computing the capacitance value. C equal to C reference, by C reference is known. Okay, C reference is known, and then Tx is the time, discharging time of the sensor capacitance, and T off is offset time, and reference time, reference capacitor discharging time. So you can always find these values. Okay, so this is depending on the RD, we use known values, V1, VTL, what we use for this. This is depending on the charging and discharging of the capacitance value. At time of this capacitance value, you can always find the capacitor. Right, you can. This is a direct interface. We are not going to use. It's simply the microcontroller. We use the microcontroller has the timer. The timer is used in this processes. Okay. So the charging time and the discharging time, like this. That's what I said. This is charging time and the discharging time. So this is used like that. You can pin 0, 2, 3. Just to mention what is the 0 in other structures. This is 2 and 3, and this is here 0, 1, 2, 3. There's some uses 0, 1, 2, 3, right? So for that, what is the condition? It is given in this table. You can refer it. Maybe short of time, I just go through this. This idea is this actually. Sensor 1, 2, 3 we can have, and then sensor 1, 2, 3 in this, the bridge types. Bridge types you have more things. So you can always compute the capacitance with this. I have given these details. You can always go through that. So yeah, we'll come back to this again. This particular charge transfer method. Okay. This microcontroller and charge transfer method. This method is similar to that because I explained that similarly. So you can have this also. This charge transfer method is the other one. I'll first discuss the other one and then come back again for the one which is important. So let's take this. Yeah. So this is for the other model. I'll come back to that and then show that what is the charge transfer method. That may be the last one we can discuss. So these are important ones, which I have told already, that you can imagine, you can understand easily this particular model. So here is the lossy capacitor model. I told you that already. So the lossy capacitor model to measure this capacitance and resistance. We will see the circuit. Actually, this is with the there is a microcontroller. The other part I told you there is a ADC and the signal conditioning circuit, interface electronics, everything. So here is a microcontroller and the display. This is for display and store. So here is your sensor. You can see the red ones are the sensors. And this is the interfacing electronics record to measure this RS and CS somewhere. So simply the microcontroller can be used in the using microcontroller and only the sensor without any interface electronics. Okay. The problem is in the charging and discharging time, you have to depend on always the charging and discharging time. Okay, so the charging and discharging time will vary, depends on the environmental temperature. Suppose there is a variation in the capacitance that will affect also. That is one problem in the case of direct interface. But we can always see that. This particular one. So here we can correlate with our sinusoidal frequency estimation techniques also. We can correlate with this. Let us see how this is done. So here is the capacitance. So we have the sensor which is connected to the op-amp. Sensor and the capacitance. The C0 is that differential capacitor. So if you have a differential capacitor, then you can connect one capacitor here and the another one here. So these both can be taken as a this sensor and differential capacitance. Okay, so here is one. You may wonder impedance to voltage converter. Here you may wonder why this particular op-amp is required. This is like so this is the input voltage which is known. Suppose that A sin omega t is known. The supply voltage you are giving. So here is the inverting amplifier which makes it minus A sin omega t. Okay, and some amplification is required. This A need not be A only. It depends on minus R5 by R5, R5 by R4. This output will be okay V01. And that sinusoidal in direct, you can even give this AC directly, AC input voltage directly here. Okay, so this is the circuit, sensor circuit. This is a sensor circuit where you have this is actually the differentiator circuit. If you see, a resistance is involved in that. It's actually a differentiator circuit. Okay, and this same sine wave is given to the quadrature amplifier. You can see I was talking about sine wave and cosine in phase and quadrature component. So here a sine wave is taken. It's very interesting to learn that this we can see the same thing in the analog. So what I was talking about in digital about this as second order generalized integrator and then the recursive DFT. So if you give a sine wave and then it can give the in phase and quadrature component, the sine and cosine component of the same frequency if you are providing the other things properly. So here is the same concept which A sin omega t in analog is this AC input voltage. This AC input voltage. Now here you get some thing because the capacitor is there. You will have the shifted output sine wave. This introduces the, if you see a sine wave, if you want to differentiate it, d by dt of sine omega t, that is nothing but you are getting here. That will be a shift in this output you will get. So it depends on what is the capacitive sensor value is. You will get a shifted waveform at the output V0. At the same time, you have R0 and RS also. Magnitude also gets varied. Okay, that waveform I can show you maybe. So this is the input waveform. Okay, this is the input waveform in this circuit. This is the input waveform, and this is the output waveform. I was talking about the shifted one. So what is the idea which behind this interfacing circuit is that sine you get the shifted output V0, and here you get the cosine waveform. The sine wave and this is a cosine waveform of same frequency. Just you see nothing is changing here. This is a quadrature amplifier. That's all. It is introducing 90-degree phase shift to the waveform. So in the program you can simply write sine omega t as cos omega t, whereas you need this all the operations in the analog. Then using the operational amplifier. So you will have the cosine waveform here. Okay, and what they do is this sine wave is taken and it is compared with the ground. And what waveform you will get here? This cos wave is taken, compared with the ground. What waveform you will get here? You see, that is going to be if wherever it is crossing 0, this particular cosine wave is above 0, this waveform this output will go to positive. huh? Whenever this it is less than that, it will go to negative. So it will generate a square wave of cos. Okay, it will generate a square wave from cos, this comparator, and this comparator will produce the square wave of sine, what is given, the input. So these are the waveforms you can see here, the input and the output from the differentiator, and the phase, in phase and quadrature waveforms. That is a sine wave whose square wave, and make the quadrature wave, and then this one, second one. Okay, in phase and the quadrature waveform are is these phases. Okay. So now these four waveforms are understood, right? Now we got these things up to this point. Okay. So then it is given to conditioning of quadrature output, and then here conditioning of in-phase circuit. So if there is any variation in this, because analog circuit you can't, you will not get the exact square wave or exact, there will be some differences. So if there is any DC shift, that will be avoided here. So what is the next step in doing here? So, okay, so what they do is this in-phase component, this square wave, due to the in-phase component and the output, these two are multiplied in this. You just see, if you multiply these two, at this point it is going to 0, and so that it is, this portion will be off. This portion will not be there in this. You can see till it goes to 1 again here. This particular half portion is clipped here. You can see when you multiply the same output with this, it is clipped, and then similarly this particular here to here, it's available. Okay, this waveform up to from here to this point is available. This particular portion is available from the output here. So it continues. So you are multiplying this output with the phase. So that's what is done here. So this output, it is switching. Switching is occurring here. So at VC, VR and VC are these two waveforms, that is in phase output and the quadrature output. So this is in phase output. Here you are getting this output, this two multiplied. So again the other channel, this quadrature and the output, these two, quadrature and output. You see this one, you can see here, this is clipped off when it is negative, this clipped off, and when it is positive, this full output voltage is passed, and then when it is negative, it is clipped off. So like this it continues. So you get the, you can also say this is a rectified waveform. Okay, this is a rectified waveform. That is what is done in these two operations. Okay, so here is you get, and here you get the quadrature output with this phase, because it is this is passed, and here this is passed. Okay, so the switching action is done, shown for on and off things. So you get this. So now if you average it out, this VOR and VOC gives the from VOR you can get the resistance value, from V where is that, V average, this V average C. So from that, this you can get CS, so the other component. Okay, VC. Okay, so from here you get capacitance component. From this you can get the resistive components. Okay, so these two are, this is if you average this particular waveform, you can get the resistance and capacitance of the sensor. So the affecting the area of this particular waveform. Okay, so for doing this, so much of electronics required. Okay, in the analog, isn't it? So and then these two waveforms are given, the average values are given to P3, here P3, and here it is given to P1. Then it computes, microcontroller knows, it's given a program to take out these values, V, RS and CS. So this gives us RS and CS values. This is CS, he would get a clock, CS and RS would be taken out from this. These are for the display. So SCK is actually the clock which should coordinate with the microcontroller and the display. Okay. So just to make this waveform, you need to go for particular so much of analog component. So or what I would suggest here is that the simple way to do it. I take the sine wave for this operation. What we can do is maybe the SOGI or the I can use SOGI or I can use this STFT even or RDFT, isn't it? The quadrature signal generators. What I take is that yes, this is required. This particular portion, where is that? This particular portion is required. So I keep this. I keep this analog circuit here. Analog circuit with the capacitive sensor. So here I get the V0. This analog circuit needs Vi input, sinusoidal input. So once I have V0, what I have to make? V0 is there as such. V0 I am not going to disturb. So V0 I am not going to give it to this here. But in phase component and I give Vi here. So this is V0. Okay. So I get in phase and the quadrature. Okay, so then you multiply to make the square wave of this, isn't it? Something multiply or multiply instead of multiplication. Even you can say just a minute. You can just compare it with a comparator with 0. When this sign in phase quadrature is greater than 0, you make 1 comparator. I am talking about in software, all these things. This is a comparator again. You get a sine wave. So you are done with these two waveforms. Sine wave is coming from here. The analog circuit V0 we are not disturbing anyway. V0 is as such. It is coming from the analog circuit, and in phase and this and this I can get it here, right? I can get it here. And after that, I need to multiply these two waveforms, right? What is that? One is from here, another one is from here. These two waveforms should be multiplied. Square wave.
Hello. Yes. Yes. Hello. Ma'am.
Yes. Yes. Any questions?
Ma'am, please kindly share your email ID.
Yes. Yeah, it is there. I'll post this material to you. In the first slide, it is available.
Okay, ma'am. Thank you so much.
Yes. So here is your in phase and quadrature component. After multiplying, I get these two waveforms. Because simply it's a multiplication. After that, you can put in as even software averager. Averager, moving averager, or there are digital average. Average it out to get RS and CS. RCS and RS, the corresponding channel, you can always look at it. So from the in phase, you get VOR is giving RS. Okay, fine. So you can get this. So you can make it fully digital. This one. That's what I'm saying. You can fully make it digital. These operations. So much of op-amp, all these things can be avoided. That's what. This is one thing. I think you are getting this one. Is it clear? This particular application. That I'm just correlating this particular interfacing circuit with the whatever the digital circuits which we have discussed already. Okay, so these two are the two things, two circuits which you can always look at to find out the R and C components of it. Okay. Now we'll go back to one more application. That would be best. to discuss. Yeah, the interdigitated capacitor or the interdigital. So this may be useful to you, an electronic level transmitter for that. So if you, it is actually a designing of an electronic level transmitter for with a digital interdigital capacitor, which I have showed you in the beginning that we have made the capacitor, right? So this IDC is used as a primary sensor. This is the sensor here, primary sensor. Okay, this particular sensor, I told you some configuration. Okay, so this is same. So with IDC length, I'm just giving you here one application of it. Okay, so IDC length is of 15 centimeter. This is finger length is 30 mm. So this total is 15 centimeter. That length total. And then you have the finger length. Each finger length is 30 mm, and the width of each finger is 0.5, and the spacing between is 0.5. So this is very closely spaced finger. So that so it is again the interdigital sensor. Okay, so that sensor is used for liquid level measurement. Okay, so the container which has the container which is having the levels liquid is H. Okay, and we have taken it through the other small tube or something, this here, and the sensor is placed. So it's again analog circuit, which we are going to talk about is now analog. So you can have always. I prefer to do this interfacing circuit in digital. Okay, I just give you this tradition, the one which is proposed by these authors, but we can always make this even digital. So this is a sensor. Now here you have the modified D-Sortis, that is a D-Sortis bridge. Which gives the voltage depends on the sensor, capacitive sensor, and this capacitive sensor already is connected, it put in the liquid. Okay, so I think you can understand this. The voltage VB is now trying to, it will be proportional to the liquid level. So that height is H. So this is a precision peak rectifier. After this, there are some process always required in this. So rectifier is nothing but that what we have seen in the previous application. Just you are making it with the rectification process. I've told you in this rectification process is like the negative off, you are cutting it off, negative off cycle. So it's a peak rectifier, and then you have a signal conditioning circuit with the zero gain, span, and gain and span adjustment, and then the output V is converted into voltage to current converter. So this is 4 to 20 milliamps current converter. Okay, so this 4 to 20 milliamps current converter. Let us see how this is. Maybe these are just a mathematics, and just give you the exact circuit that will be the actually want to discuss the interfacing circuits then. So liquid level, and then you have the bridge circuit. Okay, in the bridge circuit, one of the arm is the capacitance, this capacitance. So this capacitance is connected and put it inside the liquid. So you have the VD, VB, the voltage C and A and C, B, D. Okay, so this is your IC VB voltage you are getting here. You're getting the voltage VB. So first part is to get the voltage VB from the bridge. So always we can talk about the balancing of the bridge, and the bridge balance equation is known. So VB can be measured here. VB is this at this point. And then you have the precision rectifier. Okay, so precision rectifier output VB equal to this. See, you have the VB. The VB is now made as a constant. This K3 is that is only the constant which are not going to vary. So it depends on the input voltage, RF, and K2, some of the constants here. And this output voltage is rectified to get the DC voltage. Okay, so we here is to get the DC voltage, because it's a AC bridge. Okay, so you'll get the voltage in AC. Okay, so that this VB will be in AC. So we to get the DC from it, which is proportional to this capacitance. So rectifying it with a precision rectifier, Okay, and then there are conditioning circuits, which is that is DC output plus rectifier is converted into 1 to 5 volts standard signal using this signal conditioning, because you need to have further conversion. Here you are making it to the 4 to 20 milliamps transmitter. So okay, so that's why it is converted into 1 to 5 volts, and in that V naught is VB is, you see, the all equations, VB is equal to the V naught is just K4 plus K5, these are constants, and VB comes into picture. But VB, you have got the standard voltage again converted into 4 to 20 milliamps with the voltage to current converter. So voltage to current converter is here. Voltage, so which is giving you 4 to 20 milliamps. Okay, so the 1 to 5 volts signal is converted into 4 to 20 volts, 4 to 20 milliamps, and then the current is transmitted. Okay, actually that is for the transmitter, which is proportional to the H. This is the developed transmitter, which is linear with respect to the liquid head. Liquid head, how much is the liquid head depends on that. This current would be. Okay, so again, this is simply these are all these analog. So you can I can just give an idea to how to make these things digital. So many op amps you can avoid, isn't it? So if you want to make it a level transmitter of digital, you can avoid this particular full op amp. So my work is mostly focusing on this type of, mostly avoiding these analog circuits and make it digital as a chip. So just give this. It's an idea only. Just you give the sensor output, the sensor digital voltage output, and then how to measure this H. So these are all proposed already. Maybe for the new idea, which you can think of, that how to get it in digital level measurement in the digital. This is one application. Okay, so this is related to the one which I have discussed, the interdigital sensor, which we have made in the lab. I told you, right? So that is the interdigital, the application which is used in the level transmitter. Okay. Maybe I can give you one more example. Just a minute. There are digital outputs also. Possible to cover. This is a very simple one, actually. Yeah. So the relaxation oscillator I have already introduced. Again, you see this relaxation oscillator, how much details are recorded in, how much op amps are recorded in this. You see, we have used in our methodology, that is in our circuit design, we have used only one op amp with the capacitance and sensor. So here a relaxation oscillator with the bridge circuit is proposed, actually. Okay, so this is a bridge circuit. So where you have to, you see the capacitors CX1, CS1, CS, CE, there are capacitances. So the output at this point, you can see, this is consisting of I3, which is coming in, I1, okay, and I2. Okay, I1 and I2, the current of this bridge. CX is the sensor capacitance. Okay, so here you can have, just a minute. Yeah, CX is the sensor capacitance, which is connected in one of the bridge. Okay, so this is passed on to the integrator. Okay, so you have CF and buffer. Okay, so this is a voltage buffer. And given this particular point. So now this voltage VCF, okay, let us see this voltage VCF, which is equal to sum of these two currents, I1 and I2 in the bridge, and inversely proportional to the CF, that is the integrator anyway. Okay, so this current is integrated to get the current to voltage VCF, okay, which converter. This VCF again, now we'll see how it is used. It is depending on the Cx. The relation has been brought here, Cx and the known capacitance Cs. Cs is this capacitance. These capacitances are known. This is Cx is unknown. So it's a capacitive bridge basically. Okay, so getting this VCF of with VRB. Okay, which is the RB's. Yeah, let me see, show you the RB. Where is it? This RB, sorry, RB. So you have the subsequent part P, which is an oscillator actually. The oscillator, you have RB. So if you read it completely, so this is del VCF depending on del Cx, the change in voltage. This change in voltage is depending on a change in capacitance, and this voltage is reflected in VRB. So when we measure VRB, so inversely this is directly reflecting the changes in the Cx, whatever we have. Okay, so this capacitance pattern is Cx1 and the Cx2 and then Cs. Okay. So these are the capacitance which is in the bridge with respect to C. This is Cx, and with respect to that, these two are given as triangular type capacitors. Anyway, this is to show that it's a 3-terminal device, like a 3-terminal representation of capacitive sensor. But this bridge output waveform is not a voltage. It is this current. This current is now made into current to voltage converter. Okay, so this voltage converter again for processed for the RB here to get the capacitance value actually here. So this is one. I mean here what I want to say is here that the detector output voltage is directly proportional to the del X's. You have so many variables. You have the bridge and you have the op amps and all this circuit. So far it is being used, and these things are being used in the different applications. But maybe we can think of modifying this with a digital bridge circuit, digital circuit to get this information. This is actually especially used in the humidity sensor, this type of circuit. Okay, so mainly these are slow systems. That humidity sensors are very slow to find out. Actually, you need to take one reading of it. It takes so much time you have to wait because humidity change you have to observe, right? And these the complication is again the bridge circuit and all of them can be avoided with the digital counterpart. So we can think of that the input voltage and the oscillator output this is another application, the interfacing circuit of which contains the signal conditioning circuit of this. Okay. So this is one application, and then I think I have left with two more in this. Just I brief you what is that. The microcontroller, to coming to that microcontroller part, charge transfer method. So the direct interfaces with charge transfer. What happens is the charge transfer method. So you will have two capacitors. Okay. So initially the Cx is a capacitor which is to be measured, and Cr is the reference capacitor. Okay, we use some switches with the known voltage. You first charge the capacitor. Okay, so maybe this reference capacitor, you charge it, and then you open out this. Then you connect the charged capacitor to the uncharged capacitor, two of them in parallel. So the charged capacitor and uncharged capacitor, the charge would rearrange themselves, and it will have some voltage across the unknown capacitance. Okay, so with that you can always find out what is the capacitance, unknown capacitance values. That is what what is the charge transfer cycle. Now how many cycles it takes if you have this proper count of n and n minus 1. When you are when you are connecting this S1, when you are connecting this S2. So it depends on that, the charge transfer cycle. So basic idea is in the charge transfer method. So you have two capacitors, reference capacitor and the sensor capacitor or unknown capacitance. So this is one reference capacitor is you charge it, and then and then you connect both the capacitors in the with known voltage, okay, charged. So it quickly, the unknown capacitor, the charge redistributed transfers between the two capacitors, and you can measure, you can have the, from the known capacitance value, you can always find out what is the voltage from the known reference voltage. You can always find out what is the unknown value. Okay. So it uses the switch capacitor circuit. Cx is unknown and Cr is the reference capacitor, as I told you. Assumed to be this all capacitance are assumed to be constant during measurement cycles. So it is not varying. Okay, that is also another problem in this charge transfer method. So Cr is always greater than Cx. Okay, Vs is the DC voltage. The voltage across Cr at any n transfer cycle. Okay, so it is the voltage Vr is measured Cx by Cx plus R into Vs. This n minus 1 is the previous cycle, okay, previous charge center cycle. So present cycle can be written in terms of previous cycle. So if you keep doing that for n cycles, okay, so the closing of S3 at t equal to 0, this S3 at t equal to 0. So first you close it and charge the reference capacitor, and then close this actually. So S1, S2 to charge it, and then you open S1 so that Cr whatever charged is passed to the Cx. The redistribution occurs, the charge transfer cycle occurs in that. So any instant that VR voltage, that is the voltage across the reference capacitors, okay, it is known. So Vs is known. From that you can always find in this, all these things are known in this equation. So Cx can be found from that. That is how this Cx is found. So this is named as in n. So k is a constant and n is known, and then Cx can be computed. So how this is used in the microcontroller? Let us see here. So with the microcontroller, you have a reference capacitor Cx, and this is a parasitic capacitor. Okay. So first, in this case, you can see that the A shows the resetting stage. So you're connecting 1 and this is 0. Okay. This is 1 and 0. This is 1 and 0 here. So you are charging the capacitor C in this 1 and making it 0. See here, first it is resetting. After that, Cr is the resetting stage. Cr is discharged. This Cr is discharged. That is whatever initial capacitance value is there, it is discharged, and Cx is charged in this next one. Okay, and then you can have this. The charge B is a charging cycle. Cx is charged to VOH, the known voltage. Okay, VOH it is decided by here, and VOL is this the voltage which is so this. Having the discharging of Cr, charging of Cx, and then charged Cx is again connected, charge redistribution from charge, both the capacitors. If you one is empty capacitor, another one is charged. If you connect it in parallel, this charge from the Cx will be redistributed to the reference capacitor, and both are connected. So you can get Cx is connected to Cr. This is the third one. So this is a microcontroller. 1, 2, 3. You have. So from this, you can always, the formula with this VOL is known, everything is known, and you can find out N or Cx from that. Okay. So the idea is this. So even this microcontroller thing can be microcontrollers can be used for direct interfacing of capacitance. So that's why these are called direct digital converters. So the ones which are used with the microcontroller are the direct digital converters. Okay. So just maybe I time up. I think Satya, I just summarize.
Yes, ma'am.
Yeah. Okay. Yeah. There is only one method I could not discuss, but I mean you can have a look at it, and that is also again. Yeah. Just a minute. So this is another direct digital readout only, where you have a capacitance, and just have a look at this. This is self-explanatory, even if you just look at the slides. Even this for the impedance sensor, we have the different charging and discharging cycles using that. Okay, so the mode of conversion of C and R, two values of capacitance and resistance. That is, this is the sensor capacitance and sensor resistance are supposed to be measured with this control unit. Okay. So known values of CSRS is used in the similar way for the conversion. Okay. So this is an impedance. This is again a direct digital conversion, but they also use this op amps. That's what it is not. The literature is something different. This is for impedance digital converter. Okay. So the what I want to summarize here is that first. I've just introduced some of the ideas of capacitive sensors. Okay, so a simple capacitive sensor, parallel plate capacitors, which can have 3 plates even, and the interdigital capacitors. So these three only I have taken and shown you. With that, the capacitive sensor, how to measure this capacitance is some of the measurement techniques can be converted into time or voltage or frequency. Okay, so I discussed a method for how to make the frequency estimation for capacitance to frequency using this FLLs and PLL with the for frequency estimation, so that capacitance can be estimated. The next thing was how to use that the interfacing circuits. What are the interfacing circuits you can have with the microcontroller? Direct digital interfaces. Those are popular things. Actually, you just need a resistor and the sensor capacitance. So that's it. So you can connect it to the microcontroller and measure the charging and discharging cycles, and so you can always measure the capacitance with that. Those are direct digital converters. That can be used for measuring the lossy capacitance sensor also, and differential capacitance sensor, bridge type 1, all of them as are possible. And the microcontrollers even used with the charge transfer method, which I have discussed a little bit of that. You can have the microcontroller with the charge transfer method. Two capacitors, one is reference capacitor, another one is a sensor capacitor. So charge the one capacitor, and then the other one can be connected for redistribution. So this with the known measuring the voltage across the reference capacitor, you can always know the voltage across the reference sensor capacitance, so that CX can be measured. Okay, so that is about the microcontroller direct digital ones, and I've also given the interdigital capacitor for the level for computing the level transmission. Okay, also there's some lossy capacitor model. I've given you that you can have a level transmitter models you can develop. Lossy capacitor model, sensor capacitance and resistance of that actually can be measured with this big analog circuits, and I have given you some ideas that you can also use that you can always convert those or get rid of this analog op amps and all those things, big circuits of electronics with the digital circuits, the simple idea of a recursive DFT or SOGI. So, and with the average that is also to make it as a digital converters. Okay, that is possible. So to compare it, analog circuit, direct digital, and mixed also is possible. Analog, fully analog, you will have all of them: op amp, diodes, inductor, bridges, everything. Okay, bridge unbalance. The problems will be bridge unbalance, mismatch, op amp bias, offset, or op amp problems will be there. That's why to avoid that, you can go for digital fully. Okay, so the direct interface, you need to depend on microcontrollers there. Okay, so that is only microcontroller part. Okay, this is fully digital, or you can have a mixture of these two, where if you have a mixture, then you need a ADC and microcontroller, or ADC and FPGA or DSP. Okay, so these things are required. So here is the problem, stray capacitance, and again, once you use analog, the op amp problems always comes into picture. Okay, so it's depending on the application, so you can choose which one to go for, either fully analog or direct digital converters, or mixture of these two. So mixture of these two solutions is possible. So these are some of the references I have used, and you may even refer our papers with that. I have given only one paper here for ours, and I have mentioned some papers also. You can always search, and if you have any questions, I would like to answer. And yes, I stop here.
Thank you, ma'am.
Yeah.
Thank you so much. You have given deep insights into the interfacing circuits. Now, participants, if you have any doubts, you can ask the questions.
Hello.
Yes.
Yes.
Hello.
Ma'am.
Yes, please.
Hello, ma'am. First of all, I would like to thank you for giving such an wonderful presentation, ma'am.
Yeah.
We never felt that it was a very long presentation at all, as we were very much absorbed into your concepts, what you are explaining. I have one question, ma'am. Like
Yes.
you have said that based on the capacitance, you
Uh,
can measure so many parameters like humidity,
yeah.
the level
Yeah.
sensing, and all.
Yeah.
How is this capacitive type of sensors different from the other normal conventional method of measurement we have? No, like water level and humidity sensor and all. How it is like? What are the advantage and disadvantages of this capacitive over the conventional method of measuring, ma'am?
Yeah, actually, see this capacitive sensor now it is are the more developed circuits are available. I mean, you can connect your capacitance to, like what I said, whatever the analog circuit or the direct digital circuits. So available can be used for any of the measurement, like. Compared to level measurement always it goes with a capacitive sensor only, if I am correct. But conventional measurements, what are the things you are expecting, or you are saying about
Say,
immediate anything? So actually
let us
using
say humidity sensor if you take, ma'am. Like how?
humidity also, yeah, humidity also now. So
Hmm.
humidity sensor is, it does what is the concept behind this is, it is changing the capacitance. Actually the capacitance is varied in the humidity sensor, if you see.
Hmm. Hmm.
So
Hmm.
it's not inside. If you see what actually the physical parameter is always in the sensor. If you have a physical parameter, which may be a humidity, temperature, or anything,
Hmm.
that will be always looked into a parameter like resistor, capacitor, electrical components.
Okay.
That is a primary variable. Okay, and
Uh-huh.
then we measure this resistance or capacitance values. Just wanted to show it as is either as a voltage or current. You can reproduce it. From that,
Mhm.
there is, so this is actually, if you say there is a primary sensing and secondary variable. So primary
Mhm.
sensing is the physical humidity, which is always represented as the capacitors change.
Okay. Okay.
Yeah, liquid level also capacitance change only.
So
Okay.
then we'll have
Uh,
all
if
IDTs
you
only.
have if we have temperature, suppose it can be changed as shown as a resistance.
Yes, yes, yes.
Yeah. So these are the variation physical parameters we are changing using this. These are sensor properties simply. Okay. So how to get this sensor? How to make these variables known to us? Because physically humidity cannot be measured. We need to have this humidity watch.
Mm.
Humidity watch, this available, you can put it, and that humidity watch can work. But making as an instrument, okay,
Mm.
so to make so we need to convert that into some form. Okay,
Okay.
so some
Okay.
electrical form. So that's
Mm.
what is this the one which I presented today, the interfacing,
Okay.
how to do that interfacing. Yeah.
Okay.
Yeah.
Is there any temperature based on temperature the value of a capacitance varying or any dependency is
based
there, ma'am?
based on all temperatures, that we have to look into temperature sensors, which are
Yeah.
basically temperature sensors are all the resistance change. Okay, thermocouple, thermistors. Okay, so
Okay.
the relation between temperature and resistance is available.
Yeah, yeah. No, no, for
not not not
capacitance.
not the capacitance, not the capacitance
Okay.
for
Capacitance, no.
no, no, no.
No. Okay. Okay.
Yes.
Yeah.
Actually, as ma'am said, so
Mm.
mostly, with your permission, so I can also tell
Yes,
something.
yes, yes,
Yes.
yes, yes,
So
yeah.
because the capacitance are used mainly for humidity and level sensors because it has the dielectric medium. So the physical variables are changing, like changes the dielectric medium. So whenever the dielectric medium changes, the capacitance will change. So that is why these are all used. For example, for humidity, so the dielectric medium will be the absorbing material for moisture. So whenever the moisture changes, the dielectric constant will change. So accordingly, the capacitance will change. So that is why the capacitive sensors are used specifically for humidity and level, and the resistive based sensors are used for temperature. Am I right, ma'am?
Yeah, 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 sure,
Yes.
yeah, yeah, yeah. Dielectric is involved. That's what.
Yes.
Yeah, yeah,
Yes,
ma'am.
yeah.
That I got. What my question was, the we have normal capacitive sensor for measuring the level, as and also for measuring the density or what based on what type of materials are being used and all. As the dielectric constant will change for that. Now, what I'm saying is, so you're using an IDT, isn't it? So type of capacitive measurement. So I wanted to know the advantage and disadvantages of this IDT type of capacitive measurement with over the other, no, the normal capacitance measurement
That's what.
thing.
That's what. That is what. See, if you have some, if you want to measure something which has the water content in it, moisture in it, then you can go for IDT. So suppose soil water content, soil moisture content, okay, and water. So that all affecting the dielectric and changing the capacitance. Whereas
Hmm.
this normal one, so the normal one, what do you mean? I don't know. I don't know exactly. I'm not getting normal
No, no,
capacitor of
normal
any one example. Any one
capacitive
example.
sensors we have no for measuring the level. So for level measuring,
Level, so
I'm
yeah, a level measurement actually like that one which I have said about this three electrode type.
okay. That is
So
IDT.
you want IDT is something different from the three electrode type or two electrode type. Even you can use the two electrode type for the level measurement. That is fine. Okay, but if you want to have the IDT, you can have it in the form of the sensor which that you can have the variable capacitance values in the IDT. That is the manufacturing part is easy, that and you can have it the different shapes of it, and which you will have the more advantage of interdigital capacitances. Okay, but if you have the normal sensors that is of fixed in value. Okay, so to in order to get the change in variation of the two plate or three plate capacitors. Okay, so the variation is not much. So here if the water drop, suppose water drop is there, soil content is used, so depends on the application. You can say the water drop can affect the interdigital sensor more compared to the capacitance.
Okay.
Isn't it? So the dielectric medium is affected more by in the case of interdigitated compared to the normal sensor, two electrode sensor.
So that means the sensitivity is increased, ma'am.
Sensitivity is increased, you can say.
Hmm. Okay. The fabrication of this is done using MEMS
MEMS
fabrication.
and ANSYS
Okay.
software. So,
Mm.
yes. Mm.
Okay, ma'am.
Design
Thank you.
design is done with ANSYS. Yeah.
Okay. Okay. Fine. Thank you, ma'am.
Thank
Any other questions?
Ma'am, good afternoon, ma'am.
you.
My
Yeah,
doubt
please.
is among the direct interface methods that we discussed, which is
Mm.
the most efficient, ma'am, or which is the most widely used method?
Actually, yeah, simple RC. See, it in microcontroller based methods. The direct interface is simply based on RNC, resistors and capacitors, charging and discharging cycles. So we have to in this. The problem is if you should not have more charging and discharging times. Okay, as much as possible, you need to have less charging and discharging times. With that, you need to compute the capacitance value. Okay, I have discussed the two methods, which is one with the only with capacitance, only with the capacitance, and the other capacitance sensor. Okay, other with the different for different capacitance R and C. One with C only, and other with R and C. Okay, so
Okay.
both the methods are popular. Both the methods are popular. Direct digital methods.
Okay.
Only with the problem with the digital interfaces that you need to depend on the charging and discharging times, which is not most trustable thing.
Okay. So the charge transfer method is better.
Charge transfer is method is better. You have two capacitors, and that one is known. Again, you have the capacitance value. You need to have one more reference capacitor in this.
Yeah.
Yeah, if you have a if you have a reference capacitor, then you can use that in microcontroller also. Microcontroller direct digital also, instead of the charge transfer.
Okay. Okay, ma'am. Mm.
Yeah. So in the microcontroller, one is with C, one is with RC, and if you know it's reference capacitance, that also can be done, and charge transfer method also can be done.
Okay, ma'am.
Yeah.
Thank you. Thank you.
These are all. If you should know about the microcontroller coding, even I mean, just how to connect it and these details.
Okay. Okay.
What material is used, ma'am,
Which one?
for material for the electrodes, ma'am?
Material for the electrodes, I have to check actually. Satya, you may know. I'm not sure about this question. Materials.
I think she is asking the interdigital sensors are fabricated in a chip.
That is
Yes,
copper. That is copper.
Yeah.
Copper. Copper.
copper on
Copper.
silicon
Copper on
substrate.
silicon. Yes. Yeah. Silicon substrate. Copper on silicon substrate. That one.
Okay.
Ma'am,
Mm.
you showed that interdigital capacitive sensor for level measurement, and
Mm.
it is kept in a side glass
Mm.
uh,
Mm. Mm.
in the tank, and the side glass was open.
Yes.
So, since it's very sensitive,
Uh,
will it not be affected by the ambient humidity and
Yeah,
the
yeah,
temperature?
definitely, definitely.
We
Yes,
have
it
to
will
add the
affect.
compensation
Yes, yes, of course, of
Okay,
course.
okay,
So I have shown you how to use it for level measurement. So
okay,
the other criteria which affects this need to be compensated has to be taken care of. Yes, separately.
okay,
Yeah.
okay. Thank you, ma'am. Any other questions?
Yes, yeah.
Okay. I think there is no question.
Okay. Yeah.
Yes, ma'am. Thank you so much, ma'am, for sharing
Yeah.
your
Yeah.
valuable
Yeah.
time and
Yeah.
knowledge.
Thank you.
Ma'am, this video will be shared for the participants. So
Okay.
it was recorded and it will be shared.
Okay. No problem. Yes.
Okay. Thank you,
Mm.
ma'am.
Thank
Thank you.
you.
Ma'am,
Yes.
please,
Thank you.
ma'am, hello.
Yeah. Yes. Yes. Please.
Yes, ma'am, please kindly
Uh, uh,
share your email ID.
Actually, the video will be shared. The
uh.
all the slides ma'am presented will be shared to the all the participants. So in the first slide, ma'am's email ID will be there. So you can note it
Okay,
Yeah.
down.
ma'am. Okay, okay. Thank you so much,
Yeah.
ma'am.
Yeah.
Okay.
Okay.
Thank
Thank you.
you.
Thank you.
Thank you, ma'am.
Thank you. Thank you so much. Shall I log off? Huh? Okay.
Yes, ma'am. Yes.
Okay. Thank you.
Good afternoon, Satya ma'am.
Good afternoon, sir.
Thank you for joining us.
Thank you, ma'am.
Welcome you, sir, for this session.
Thank you, ma'am.
Sir, we will just wait for 5 more minutes, sir,
Sure,
then we
sure,
will
ma'am.
start.
No problem.
Okay, sir. Thank you, sir. Sir, I think we can start. Yes, sir. And this is for your kind information. And the audience are mainly faculty members from different colleges and universities, and others are research scholars at PG and PhD level
Right,
mostly.
ma'am.
Yes, sir.
So shall I start?
Yes, sir. Let me start. Let me give an introduction about you. Then we can start.
Okay, ma'am.
A very good afternoon, everyone. I welcome once again our today's speaker, Mr. Satish Kumar from CSIO, Central Scientific Instruments Organization, Chandigarh. And we can start our session with a brief introduction about Mr. Satish Kumar. Mr. Satish Kumar started his career as visiting faculty at D. Crest Murtal from September 1993 to 9th May 1994. He has joined CSIO Chandigarh in 10th May 1994. He is currently working as Senior Principal Scientist and Professor in Academy of Scientific and Industrial Research. He is also honorary faculty at Indian Institute of Engineering, Science and Technology, Shibpur. He has worked on various R&D projects as a project leader and has expertise in the area of automatic target recognition and early warning alert system, etc. His main contributions are earthquake warning system, vehicle detection and recognition system, intelligent movement detection system for human and elephant, etc. His current research works are AI-based seismic signal analytics, intelligent systems for border security management, automatic target detection system. He has published 70 papers in various referred international and national journals and conferences. He is having 3 patents and 2 copyrights. He has been conferred various prestigious awards such as Raman Research Fellowships during 2009 to 2010 to do research work at Geophysical Institute, Germany. First prize in CSIR Leadership Development Program in 2014. NRDC Meritorious Innovation Award in 2015. Transformation Innovation Gold Medal Award 2017. Top 51 Technologies Recognition at India Initiative Innovation in 2017. Best Technology Award under Smart City theme at India International Science Festival at IIC in 2017. Scotch Order of Merit Award 2017 for Earthquake Warning System. Scotch Order Merit Award 2018 for Automatic Target Recognition System. Jury member of Smart India Hackathon Hardware Edition for 2018 and 2019. Jury member for HCL's Worldwide Initiative Technovations Exchange Artificial Intelligence in 2018 to 19. Certificate of Excellence in Recognition of Work in the Field of Disaster Management by Institute of Disaster Management and Fire Sciences, Chandigarh during Suraksha Ke Sitare program on 25th May 2019. Best Paper Award on Fusion of Visible and Infrared Images for Victim Detection at Symposium on Optics and Photonics Based Technologies and Instruments for Civil Society, Optics 2016 in 21st October 2016. He is also a member of Board of Studies at UIET KU. He has been delivered various invited talks at premier institutes and universities like PEC, NITTR, DCREST, UIET, RIT DAV University, CGC, Khalsa College. He is life member of Indian Society of Systems for Science and Engineering and member of IEEE. We are really happy to have you in our session, sir, and we can start the session now. Please, sir.
Thank you, ma'am, for introducing me.
Welcome,
And
sir.
I am also welcoming all the participants from the different part and also from the different colleges as well as students also. So first, kindly let me know whether my screen is available or visible or not.
Yes. Yes, sir, it is.
It was visible.
Yeah, no, it was visible now. Yes, it is visible now.
It is visible.
Yes.
Okay,
Yes,
ma'am.
sir.
Am I audible also to all and visible to all?
Yes, sir. Yes.
So really, I am thankful for joining me for this session. And I have seen that you are from the last 2 days or 3 days, you are going for recent advances in sensor design and interfacing circuitry, because this is the area where a lot of innovation and things are going on. But today's my specific talk will be related to mainly, these are the different sensors are there. These are the different system. What can be the possible applications? Rather, I will initiate some of the research area which you can take up, which you are thinking that this can be add on to this certain kind of a layer of intelligence, certain kind of a networking, certain kind of a signal processing. There may be image processing, there can be embedded technology. So I'm trying to make mainly towards the industrial application, and main target, whatever the theory that need to be connected with the actual industrial application, which is the current need of the hour. Because sometimes we know about the sensor, right, but we do not know how we can interface to give the technology. And the nowadays people are interested not only for a one parameter, people are interested for a n number of parameter. From similarly for the health index, people are not interested only for the blood pressure, people are interested also for at different time different parameter. Similarly for strategic security surveillance, we are not interested only the image which CCTV camera is giving, because powers are very power hungry device are there, lot of computations are required, lot of intelligence are required. We are always targeting for a particular target. There are a suspicious layerness is there. So how most of the parameter is going to give you a intelligence system for the different technologies, different users, and also for the different sectors, which is the today aim of my talk to you. So if we will start with this, theory of technology evaluation, and you are aware of that, always there are different stages of the technologies, right? Everywhere we talked about the tool, what kind of tools we are having. Whether we are talking about if we are talking about the mechanical engineering, then different engineering tools are there. If we talked about the electronics like circuit makers, even the different kind of tools are there for making the circuit validation as well. Similarly for the computational tools, so tools, machine, and automation. Nowadays there is an era of an automation where we do not want to do, machine itself is taking decision. It is adaptive in nature according to the environment. For example, AC is there automatically as per the temperature is changing, so need of the user is changing. Similarly, if we are going to have a camera, it's not only recording a particular camera, but also recognizing a particular thing, also recognizing a particular event of our interest. And not only this recognition, but automatically dissemination is there. And it is because physical labor, because enormous amount of data being generated. It is very difficult to handle all kind of a data, but actually we are interested in the knowledge generated from the data. So what exactly we are doing, we are going to have a great degree of control over the natural environment. Whether we talked about the air quality, whether we talked about the biomedical, whether we talked about the agri-related parameter or environmental related parameters. So there is a lot of control over the different kinds of a degree of environment. And we know survival of the fittest. Nowadays there is a challenge because everybody needs, user demand is also increasing, and it is not feasible without the convergence of the technologies and also the multi-sensing, multi-parametric, which we are going to discuss in the subsequent slides. And there are certain kinds of landmarks in history, we are aware of that. Agriculture, invention of the wheels, mass transportation. But the important one which has given us a boost in the area, that is ICT, information and communication technology, where people are demanding more storage, people are demanding more processing, where there is a mixing of information technology, electronics, communication, computer, and sort of so many discipline is coming together to give a technology to the user. Where our demand is also nowadays, everybody want they should get information on their mobile. If some kind of a alert is there, they should get a alert on their mobile. Health index also they should get on the mobile. Even if they are going to home or they are leaving the home, then automatically switch on, switch off, means so many things. Even kids are there, so they want to monitor what kind of a thing, what kind of a state they are. Even the elderly being are there, so they want to monitor on the mobile. So the ICT is playing a very important role and also affecting the whole spectrum, all wheels of the technology in every corner. Whether it is we are talking about the society, or whether we are societal application, or we are talking about the strategic application. Why we are doing all these things? Because ultimately the technology, economy and society, these are very important thing for any, whether you talk about sensor system technology. So always there is an economic growth. When economic growth is there, there is always a need. Because need, sometime, there are two ways. Sometime market is giving you need, sometime user is telling this is my need. So there is a competition is there. So need sometime coming from the market and sometime coming into the market. And this is a very different thing which user, because once it is satisfied, it's one more dimension it required. There are domain knowledge, then finally what we are going to make, we are going to have a knowledge society, we are going to have an industrial society, we are going to have a networking of society, and there are different innovations are there, adding values are there. So ultimately from application paradigm to the technological paradigm we are going to have. And the economic growth, because economic growth is only feasible because of the research. Without the research it cannot be possible. And we talked about the information and technology. So always what we try to do from the traditional knowledge, we are trying to achieve our goal. And with the help of information communication tools, predictive behavior, diagnostic behavior, descriptive information, so lot of things we are going to incorporate. And what to be done, how to be done, where to be done, why to be done, there are a lot of questions we are going to answer for a different kind of a sectors and for different kind of applications. So people are saying now IT, we talked about the information and communication tool. People are talking about the information society, and people are saying IT has a full swing. Rather, people are start saying that our IT sector is saturated. But I am saying IT sector has not been saturated. Even if we talk about the Indian perspective point of view, so still we are lagging. You can see the information society, whether disasters is there, health is there, you are aware of that. We have not utilized our information society or information technology in the area of disasters. For example, still if we are moving to a hillside, if there will be a landslide and there will be a traffic jam, we are not getting real time scenario, a alert, don't go on this path, there is an disaster is there. If there will be an earthquake or there may be tsunami or cyclone, whether that kind of early warning system or just like alert we are getting on our mobile phone, it's not there. Similarly, health is very important sector, and rather people are saying the health is going to be, because now we are not interested only for the health, but also routine monitoring, even the healthy one. It is not only related to the patient, but also it is related to the normal person who is interested to know what are the various factors. And mobile is going to be play a very important role in coming future, where lot of features can be processed, computed, and real time information can be generated. People are interested in energy, right? A less energy is there, if it is required activation, deactivation, how to take care of the energy, right? Energy generated not only from the solar, but what are the other means of this, mainly for the strategic sector when there is a crucial time is there, energy should have been there, the activation deactivation of the system. Similarly, the climate is changing, because if a soldier is moving nowadays, China conflict is there. If our soldiers are moving, we should know exactly what kind of climate change will be there, how much snow will be accumulated, whether there will be an avalanche will be there, because prediction of an avalanche is going to help. Similarly, suppose avalanche happen, whether we are going to trap the soldiers, you are aware of that, lot of mishappening is going on, but still we are not having a technology where easily we can trap. There may be some kind of a band, technological band, which can transmit it, we can locate our soldiers. Even not only the soldiers, our weapons, our other thing may goes into the snow. So that kind of a thing still it is lagging, we are not able to give to the users. Similarly, for the agriculture, we do not know, we heavily depend upon the rain, sometime heavy rain, sometime you are aware of that when snow is falling. So even we cannot predict accurately whether we are going to have problem of this year. What are the alternative means are there, right? If flood is there, then how we can utilize that water? If water is not there, how we can do that thing for the benefit of the society? Similarly, there are water, weather, so many application is there. So ultimate aim, I am saying, the ICT has not been implemented, the information technology has not been reached mainly for our country point of view. So there are lot of innovation, there are lot of gaps are there where a people like you can work together to give a technology to the society. And you know why we are saying a lot of things are being coming up? Because of the computational platforms, right? Even if you are aware of that hardware platform you talked about, it is miniaturized, right? ARM and many processors are coming up. Even there are certain kinds of a tool which is NVIDIA tools are coming, which is helping you not only GPUs but also the machine learning, real-time vision processing are there. So many scientific tools are there, fast computation. So there are different kind of a computational platforms are available, which is motivating us to do the new things for the user, so that a lot of multi-sensing, lot of sensor which we will see in the preceding slides, so that it can be incorporated into give the user a valuable information. And if we talk about the intelligent system, the question comes, because why specifically I have taken this slide. This is mainly for the student point of view, because when we came to discuss with the student of a computer science, he is thinking that only programming is his area. And if we talk about electronics, he is saying communication or hardware. Means mechanically he is saying I have to take care for the door design and all these things. So, but they are not ready to interface with the other discipline. An intelligence system cannot feasible without the meeting or without the teamwork between the different kind of a discipline. Like material science is also nowadays a lot of innovative materials are coming. For the strategic point of view, microwave absorption so that it should not be detectable by the camera, right? So many, even you can see mobile phone. A mobile phone is a best example where not only physics, computation, electronics, material science, nanotechnology, classical optics, all these things coming to a picture and giving us a intelligent system. And you know it is not feasible. See, if will not join, then we will be isolated. We are not going to give a good technology to the user. Therefore, at least the conclusion drawn from the other engineering, other discipline should know. Otherwise, we cannot work together, or there will be boundaries, and we will not deliver as required in the current scenario. And when we are saying the intelligent system, the question comes that what are the intelligent system requirement? People are asking nowadays lot of intelligent system available. Then what is the need of doing research in that area? So there are certain issues. There can be many few I have highlighted. You know, need for the knowledge based system design, lot of data being generated. Even you know cameras are huge. Even Delhi, you are aware of that, more thousands of cameras being installed. Even MCD is not aware of that what to do with that data. But data is a wealth, right? Lot of information can be derived from this. You might be aware of that Mumbai Worli bridge is there. So lot of accelerometer sensor has been installed there, from the bottom, from the top, and huge voluminous of data being generated. But it is a dumping of a raw data. So we need now a knowledge based data where something can be extracted, so that a planning and some kind of information can be extracted from that data. And also when we talk about one system is there, you are aware of that, just like we are having a mobile phone, we need another. We are having TV at our home, we need another. Why? Because of many other feature which we are looking into. For example, the issues are speed. If you are taking care for the image processing, real-time image processing, then you are aware of that speed is very important. And sometimes, for example, you are talking about the acoustic signal processing. So microphone you are using, you are aware of that sampling rate of that is going up to 20 kilohertz, 10 kilohertz. 10 kilohertz data, if you are taking, your sampling rate is 10 kilohertz or 15 kilohertz. You are aware of that in 1 second you are having 15,000 samples you are having. And in that sample you are going to have an filtering also, you are going to manipulate also, you are going to have a statistical feature also, you are going to have a window based some certain kind of computation. so that how much window moving kind of a, it depends upon what algorithm you are going to perform. So the speed is an issue, because you are aware of that real-time system. If we talked about real-time system, we talked about either it is a hard real-time system or it is a soft real-time system. You are aware of that because you all are faculty member. You are aware of that. Real-time system can be defined as not only the logical correctness, but also the timing correctness of the system is required. And soft real-time system means up to that time the task should have been executed. Hard real-time system means it should have been executed exactly at the t time, minus the delta t plus delta t is a failure of the system. For example, we are going to have an environment where we have to hit a missile, right? A missile can be only hit at a particular t time, which is estimated time, and without that, there will be either it will go away, both the side it will be waste. So it's a failure of the system. That is why our computation speed is playing very important role. Rather, sometime our system is having edge if we have to optimize this kind of a thing. Another thing is a data storage. See, now as the technology, the tools are increasing, our greed is also increasing. Sometimes people are talking about the thresholds, right? Sometimes system get trigger and then only it is recording. But nowadays people are saying memory is not limited, it is unlimited, right? So I am not interested only, I am interested in triggered parameter, but I am also interested in continuous data, the raw data. So I am talking about a different type of streams. When the people who is talking about the data acquisition system and a sensor is being there and some algorithm is being performed, so they are aware of that. Now people are talking about n number of streams. One stream is a continuous data, raw data being stored. Another parallel, see, I am saying when it is a parallel, algorithm is also processed, then threshold is being applied. Take care of the acceleration, right? Continuous acceleration is coming. Footsteps are there, right? So continue data also we are recording, we are also recording on the basis of threshold. Now some person may come, okay, I am not interested, I am interested in the RMS value. If RMS value is greater than that, then it should be, it is the third stream. Sometimes people are saying I am interested in time stamping, right? At this time, minimum this recording should be there, right? Sometimes people are interested okay, if temperature is 25 degree in a plant, then I want a complete recording. So now you see how many number of streams are there, data storage is there. When you are designing a system, starting from a simple data acquisition to a very intelligence one, when we are having a information, when we are having a processed information on the basis of algorithm. And sometimes not only one algorithm. For example, sometimes person is saying, if I recognize a vehicle into a zone, right, then I should record. So it means once num data is to be logged, right, then at the background the recognition detection algorithm is being there. Once it is detected, then we have to recognize a vehicle is there. Once vehicle is there, then we are going to store the parallel kind of a thing, right? So this is very important thing. Another thing is a data handling capability. When you are having a multi-sensing data, when you are having a multi-sensing approach, there are vibration sensor, there are temperature sensor, there are vision sensor, there are thermal imager also there, right? There are sometimes there is a UWB radars also there. So how, and they may be operated in a different sampling rate, right? For example, a vibration may have a 100 sampling rate, but acoustic may have a 5,000, 10,000 sampling rate. Similarly, your camera may have a 30 frame hertz, right? Your camera may have a 60 frame hertz. But what you will do with the 60 frame hertz, you have to optimize how many number of frame you are going to process in a 1 second, because you do not have time. You have to process 10,000 acoustic sample also, because time is same only. Every second, your load, your computation, everything is increasing. So that need to be taken care. Another thing is the mixed signal situation. You are aware of that mixed signal. I am talking about vibration, I am talking about camera, I am talking about radar. Sometimes independently they are working. Sometimes we have to see primary sensing, secondary sensing, tertiary sensing. Why? Because power is an important thing. We should see which sensor is taking less power. Once it is detected, then only we are activating the other. Otherwise, there is an active and passive. We will make which one is a primary, which one is a secondary. For example, you take an example of any campus, right? Campus, we want a complete surveillance, right? If cameras are there, if you are making 24/7, you are aware of that number of frame generated. Then computation are there where raw data is being generated, whether you are detecting and recognition of a man, right? And instead of that, if we will have a footstep sensor, which is not having any power, and if something is detected, some vibration is detected, then only we are activating a camera. And it can be false also, depending upon. So you say how many times? Maybe 10 times, maybe 15 times, but not 24/7. So what we are doing, we are not only saving the processing, but we are saving the computation power as well as the actual power required. Another thing is a real-time environment. Now, there are two kinds of a research are there. One research is in the lab, where offline, whatever we are measuring, data is there, we are computing, right? We are doing so many algorithms. Time is not a problem. Environment is not a problem. But try to see if we are talking about a real-time system, which has to work in a environment, real scenario where there will be humidity will be there, and for example imager is there, there may be rain. You are aware of that during rain your thermal imager may not function well. So at that time, if your system is dependent only on the vision, right, this system is going to give a fail during the fog. Not only fog, when temperature is equivalent to the environment, or when there is a rain, it will be fail. So whether there are other modalities are there. Similarly, when there is a humidity, when there is a fog, or when there is a temperature is very high, when there is a night temperature is there, right, rain is there. So all kind of a weather, real time environment, we should think of a technology, we should think of a sensor, we should think of a system which is going to give the different kind of an information. And encryption and decryption is required. Why it is also required? This is a security protocol. You know, sometime you talked about the early warning system, and you are going to take a important action on the critical installation, strategic installation, right? At that time, some malicious network or person may enter to the system to generate a unwanted command. So at that time, our data should be encrypted and decrypted in a well manner, so that other person should not have an access to our network as well as data. Another thing is a dynamic configuration. Dynamic configuration, you see, I talked about a one system surveillance of a campus. I am saying once vibration is there, then only I am switching on my camera. So I am saying when it is required dynamically, it should be connected to a network. Initially, only the sensor, vibration sensor with the network. But once it is connected, so all these things are processed together. So dynamically configurable as and when it is required. Or sometime, as I told you, when something happened, we are recording temperature, time, so many times stamping we are taking care. Next is a hot standby. This is the best example which we are discussing, that camera is a hot standby. If our algorithm is detecting the presence, our energy is high. Similarly, the detection of a person is also acceleration based, velocity based, energy based, statistical variation based, so many things. So our camera is in standby, and there can be acoustic signal, right? There can be other signal which we can look into. So what actually is a need of the hour is the demand of a convergence of a technologies. There are certain technology where not only the chemical sensor, physical sensors, they are coming together to give a derived quantity. And sometimes our mathematical models becomes like that, is sometimes we are not getting authentic result. So what we are doing, we are going to have a one more parameter, right? There are many various tools are there to optimize this thing. So ultimately, there is a demand convergence of the different sensing modality and to give the intelligence system to the user. So the first question comes when we talked about the sensor and system, definitely comes into our mind that if we talk about the sensors, why we call it a smart sensor, why we call it an intelligent sensor, right? Smart means what, intelligent means what. So smart sensor is, normally we talked about the digital things when we are having a digital interface. Smart sensor is a combination of sensing element where our data is converted into the digital form and a bus interface in a one housing. Here I want to tell you ADC, normally people are asking how much digitizers of ADC you are using. The person who is into the field, they are aware of that 8-bit 12 bit, 16 bit, 24 bit, right? And as your digitization is increasing from 8 bit to 24 bit, 2 की power 24, you are having a 144 dB kind of a signal, which is equivalent to the noise. Is very difficult to handle that situation, right? Because it is a nanovolt kind of a level we are going, minimum LSB we are talking about. And also you are aware of that when we talked about ADC, you are aware of that one is a multiplex ADC where, for example, 3 channels are there. If 300 sampling rate I am fixing, so 100 sample rate for each channel, it is divided, right? But suppose I am having a temperature sensor, I am having an acceleration sensor. What I will 300 mean 3.3 millisecond, right? And 3.3 millisecond temperature will not change. I am not interested to overload to my network with the temperature in every 3.3 millisecond. I want after 1 second temperature to be logged, right? So why should I have a multiplex? I should have a parallel ADC. Then only I will have a different sampling rate. And for the student, sometimes people are asking, can I have a different multi-rate system with a single ADC? With a single ADC, if it is a digital sensor, digital system is there, with single ADC, multi-rate is not feasible. It is feasible if we will have a parallel ADC, then only different sampling rate. One chip can handle only the similar kind of a sampling rate. And sometimes people are asking Nyquist rate, sampling theorem, all this is related to this. And bus interface, why I am saying? Because ultimately this data is going to connect somewhere. Sometimes people are talking about PC architecture. So people are talking about EJA bus, PCI bus, PCMCA bus, USB bus, right? Even if sometimes people are talking about the strategic one, they are talking about HP, GPIB bus. So different kind of buses are there. So intelligence sensor, where we talked about, there are several functions like self-testing, self-identification, self-validation, self-adaptation. Sometimes automatically evolution computing is there. So sometimes automatically a person is recognized. I'm giving you a very good example. If you are going in a mall, right? A camera is there. It is particularly looking at a particular door, right? Who is entering? It is keep on logging. Suppose I am saying it is an intelligent network, and in that there is a layer of a intelligent algorithm which is going to tell whether the concerned person who has entered is a suspicious one or not, right? This, I am changing the complete dimension of a camera. Currently we are having a CCT camera, that is a very cheap camera, everywhere it is available. What it is doing, it is continuously in a static way, it is looking for a particular point, and whomsoever is coming, it is logged. There is a data logger, continuously data is being recorded. Now I am saying, okay, I have inbuilt a layer of intelligence where I am going to have a suspiciousness of a person. If that suspiciousness person has been detected, then PTZ kind. So now it should not look to that point only. Now it has to track that person. Wherever he is going, he is tracking the activity. Now you can see, if we are having a simple camera and we are having an intelligent camera, how much computational load, how much computational efficiency, efforts and cost also is changing. So this is the need of the hour for each and every kind of a thing. So a smart sensor where we are talking about, there is a signal conditioning. This is very important part, because sometimes there are a different kind of a levels are there, right? Sometimes you are saying my signal is not being triggered. For example, there is a vibrations sensor, and if you are jumping near the sensor, it is not being triggered because of the level into the signal. That need to brought to the ground level. And there may be sometime gain is there. Sometime when you are processing a data, everybody is asking, when you acquire the data, whether there was some gain is there or not. Because when we are having a temperature sensor, right, a temperature is always recorded in form of a voltage, but ultimately it is to be converted into degree centigrade. Similarly, if you are having a velocity sensor, then you are getting a voltage. That voltage is equivalent to the volt per meter per second. That is actually the sensitivity of the sensors, right? For example, per degree, per volt per degree means this volt is a this much degree. Similarly, if velocity is there, this volt per meter per second. Similarly, acceleration is there, you can talk volt per meter per second square. Similarly, pressure, like that there will be there. So question arises that if there will be a gain is there and you are considering that temperature, but twice of the gain you have applied. So you have to take care gain into the processing of data. If you have not taken care, then you are going nowhere because already the signal has been doubled. Similarly, there are different kind of a thing. Sometimes people are interested low pass filter at the signal conditioning level also. Sometimes people are interested at the DSP level. So we have to see whether we are talking about a signal conditioning level, whether there is a single ADC is there or not, or whether there is a multi-rate system is there. If multi-rate system is there, there will be n number of ADCs will be there. And ADC will be there, can be 8-bit, there can be 16-bit, there can be 12-bit. Sometimes ADC may have a number of, there is also a cascading low byte and high byte. So that need to be taken care. And ADC is also there. Different technologies of ADCs are available. Sometimes what it is doing, it is giving the lower byte, higher byte. Sometimes it is a serial, it is giving data. Once it is there, flag is there, now you can read. Sometime it is giving it after 1 second, then only access will be given. So you have to maintain a buffer. Once buffer is full, then you are having access. Again, you start doing this. So reading of that is also a challenge in a buffer ADC, because once you are reading that, if it is overwriting, then either it is not able to write or you are not able to read. So a proper mechanism handling at the sensor level, at the signal conditioning level, at the ADC level, circuitry level, you need to take care. Another thing is an application algorithm. As I said, human is there, vehicle is there. So sometimes people are interested in energy based algorithm. Sometimes people may be a statistical algorithm, sometimes RMS value, sometimes only threshold for a particular window, say for example 0.1 second, right? Another thing, data storage. Data storage also having, there can be a raw data, there can be another trigger data. So where raw data to be stored, where which data to be stored. Another important aspect here need to be taken care. Suppose we are having a data storage, always limitation is there. If it is going to full, what to be do, what to this system will do, whether it should wait, it should stop recording, or there will be again a just like a cycle, overwriting will start. And then overwriting will be start, then LRU algorithm come into the picture, least recently used, right? So what kind of algorithm should be there? Another may be there, if it is a 70%, 80% full, it will alarm if my memory is going to fail, or there can be alternative buffer need to be maintained. So these kinds of an important thing we need to take care when we are designing a smart sensor model. Another thing is that local user interface, how we are going to communicate, whether our sensor is having computational capability, it is only informing to us to our network or mobile, then each and everything the hardware interface, because we are not interested into overshooting and undershooting, because sometime for example a vision camera we are taking and our processor is not enough to handle that much speed is there, right? And sometimes people are having very good speed is there to achieve. Sometimes we only need to have a temperature sensor. Why we need that kind of thing? So a optimum thing, because and one of the important aspect is the power consumption, because whether this is a offline instrument, it is to be worked in a lab or it is to be worked in a field. If it has to work in a field, whether power is a problem or not, because always power may not be available, solar may not be available, then what you will do? Similarly, take care of a best example of a snowbound area, right? Whatever be the instrument we are having, we have installed now over the 6 months, we are not going to have access of this instrument, right? If power fail, you have to see a 6 month kind of a data we will waste, and then we have to wait for another year. So these kinds of a thing need to be taken care. And another thing is a communication. Communication is very important aspect, because now information need to be communicated. What kind of a communication you are having? You are having dial-up communication, you are having GSM communication, you are going to have a VSAT communication, or nowadays people are also having a LoRa communication, or sometimes people are also having a spectrum communication. You might be aware of that spectrum communication, it do not require any kind of licensing, right? It is working on a 2.4 megahertz if we are talking about the commercial one, and 900 megahertz for the military kind of a thing. So but there again problem comes of a antenna, because a small antenna of a lower gain you cannot achieve a more than a 500 meter kind of a communication, But if you want to achieve 10 kilometer, 20 kilometer, then you need to have a 12 dB, 14 dB. Again, the question comes whether you are having a circular antenna or you are having a unidirectional antenna, because the gain, it is wastage in the circular one. So you want a unidirectional antenna. So these are the different kind of a thing. Another thing is a network, whether we talk about a LAN or it's a VSAT base, where actually these sensors are being connected, whether there is a common bus or whether the process information, what protocol we are going to have. So this is very important to understand. So there are different levels of intelligent sensor processing. Intelligent is first is a data acquisition. Data acquisition itself a biggest thing. If electronic people is aware of that, how to get connected, how sampling rates are being taken up, how different samples being taken care, how different rates we are going to have, how different kind of streams we are going to have, where we are going to store. Then sensor compensations are there, because there are lot of crosstalk variations, lot of filterings kinds of it. So lot of sensor compensation we are going to provide it. And it is also hardware based, it is also software based. Sometime detrending, lot of things pre-processing we are doing in the software also. Information enhancement means whatever be the information we are deriving, we are going to generate the different features so that the hidden information which is not being taken care so far is being taken care. So ultimately we are generating a knowledge from this data, and that knowledge is very important, which we talked about at the initial level, that knowledge base is important rather than simple database. And if you see the different kind of stages, data acquisition stages are there, transducer are there, amplification, I told you about the gain, right? Because sometimes gain is very important, you need to take care. Low pass filtering, because if you are aware of that, if footstep you are going to take, footstep is of a low frequency in nature, like 10 to 40 hertz signal only, then why to record for more than 100 hertz? So you can make a low pass filter where you can only record a vibration pattern of a lower thing. Similarly, if you are interested to record only of a cutter can be of a particular band of a 1 kilohertz. So accordingly, you can optimize your data, that which data need to be taken care. And A to D converter, what is the digitization, whether 8-bit, 16-bit, 24-bit, serial processor, serial ADC, parallel ADC, how it is going to take, whether multiplexed or multi-rate. Similarly, sensor compensation, calibration, linearization, signal integrity, diagnosis. So if there is a problem, whether it is diagnosis. Similarly, there will be information like noise removal, sensor fusion also there. Why I am saying sensor fusion, we have taken an example where vibration sensor, acoustic sensor, and thermal sensor is going to give us a surveillance of a campus. Similarly, knowledge extraction, pattern recognition, in our example which we discussed, recognition of a human, recognition of a vehicle. This is very important. Even sometimes people are doing PhD only on this topic only. Real-time recognition of a vehicle, real-time recognition of a people, right? Because it is in the motion. When it is the motion, sometimes front portion is available, side portion is available, sometimes partially, sometimes occluded thing is available. So how we are going to have, what kind of a morphological operation we are going to perform, right? If we have performed that, how we are going to do recognize this thing. Again, if face detection algorithm need to be performed, it is very difficult, because you are aware of that our accuracy will not be up to that mark. Again, think classification. Suppose you want to classify between uh, different kind of animals, right? Again, it can be a problem. If you want to classify between the different kinds of a vehicle, whether it is a low vehicle, light vehicle, medium vehicle, or heavy vehicle, then again this is a great challenge, because scale variations are there, right? Your depth variations will be there, your angle variations will be there. So even the resolution may become a problem. So lot of things you need to take care if you are taking care about the classification of a new knowledge extraction. And the predictions mean early warning or predicting something. Predicting means whether that person who is approaching to our campus can be dangerous, or it is a threat will be there to the organization or not. Similarly, for example, if a troops near the China border it is coming, whether that can be a threat to the us or not. So that kind of a prediction is required. Adaptive filtering is very important, because sometimes the similar, our noise level is being changes, day is different, night is different, middle day is different. Similarly, in image processing, sometime there may be people are moving, so it cannot we can not consider a background as a static, because if, for example, take case of an uh, road scenario, you can take in road a lot of people are moving, then how you can have a static background filtering when you are having a detecting a person, so or detection a change, so it should be adaptive in nature, then only it is feasible. So ultimately what we are going to do, what we are going to have a sensor and system, accurate data and better decisions we are going to have. So now there is one more layer, WSN, where people are talking about we are having a nodes and it can be applied. For example, take care of a structural health monitoring system. When structural health monitoring system is there, our ultimate aim is to find out the damage detection, then damage localization is there. And then we can say whether retrofitting is there, and number of sensors are required for a big building. If green technologies are coming, then WSN is a part. It is mandatory to embed this kind of a sensor into the bridge, into the buildings, so that the health of a building is to be continuously monitoring. And here operating system, sometime operating system is also important one. Customize CE, or very modular operating system need to be taken care with the hardware, that it will only take care for the functions which is required. Otherwise, it will be an overhead, will create a problem to you. And network protocol, power management, filtering signal, memory. So all these things will be embedded into a single chip or wireless sensor network. And if we talk about the wireless sensor network, am I audible? Don't you face any problem? Hello?
Yes, sir. Yes, sir.
Okay,
It's
okay, okay.
audible.
Okay, okay. So if we talk about a sensor, also there are small size, and sometimes there is a large size. But small size is a MEMS base, right? But MEMS are having sometimes sensitivity problem. So you need to see whether your application need a sensitivity is an important factor. So miniaturization is important thing, or accuracy is important thing. Radar and satellites are different thing. Similarly, whether you require small in number or large in number. For example, in case of a campus, you are aware of that we talked about primary and secondary sensing. Primary sensing, we talked about the vibration. So vibration sensor may required in large number, depending upon how much area it is going to cover. Another thing, whether we want to have a only particular zone to be covered or entire network to be covered, right? Accordingly, our number will be there. Similarly, whether there is a passive sensor or active sensor, I told you passive do not require any power. Like for example, seismic is nothing but it's a vibration sensor, so it do not require any power. But active sensor is like our radar, our imaging. Similarly, acoustic sensor, they need a power, right? So once something is there, then only we. Similarly, heterogeneous and homogeneous, they may be of similar kind, different kind of things may be there. For example, n number of vibration sensors, same array kind of a thing. Then there can be different kind of a sensor, acoustic sensor, temperature sensor. Heterogeneity will also be maintained. Sometimes there is a fixed, sometimes ad hoc, sometimes fixed, only fixed number of sensors are there, but ad hoc some are available at the different time. Similarly, dynamics, it is a stationary, sometimes it is a movement, mobile, robotics are there. And the best example is that some debris is there. If a person is trapped, so it is mobility sensor will be there. Or some gas, hazardous gas are there. So according to the situation, lot of sensors are being dynamic in nature. And another thing is that sensing entity, whether we talk about localized, we are talking about distributed. For example, environment monitoring is there. You are taking care of the oxygen, nitrogen level, pollution level, you may be interested. You may be interested what is the temperature variations. You may be interested in radiation, right? So many things nowadays being taken care. Another thing is the localized bin target tracking. I talked about in a mall, if a person is looking, a camera is looking into a system, a person of a suspiciousness is there. So now it is going to track that only. That is localized in nature. Similarly, mobility, whether it is static or dynamic, is there, right? Static mean everything is fixed. Dynamic, it is being changing as per the need, as per the application. And operating environment, I talked about whether you are working in a gaseous environment, whether you are working in an open atmosphere, whether you are working in a lab environment. Another thing, normally technology being divided into three regions. It's a snowbound area, It's in Punjab region kind of a thing. Another one is a Rajasthan where desert is there. So what will be the operating conditions will be there? Accordingly, your challenge will be different. Because when snow will be there, your wire, your signal, everything will be there. And if you are going to have a imaging, then there can be dust. How you are going to acquire the image? This can be a great challenge to you because intruder may come when your camera is not able to see. Even if you acquire the picture, you are not able to capture that. So you need to have a other environment, other sensor as well. Another thing is a communication, whether it is a wired one or a wireless one. If wireless one is there, again it is required active. You need to be have some power is there. Again, if it is not available, then your data will be lost. If it is strategic in nature, you can aware of that. If it is not working or range is not coming properly, you are aware of that. If a concrete environment basement is there, we are not able to communicate. Similarly, bandwidth, whether it is a high or low, we have taken an example where vibration footstep is a 100 sample, but if acoustic signal is there, it is 10 kilohertz. So bandwidth can be small, bandwidth can be high. Similarly, for a network, if we are transmitting, whether we are transmitting kilobyte, 1 kilobyte or a 10 kilobyte or 100 kilobyte 1 second. So accordingly, our bandwidth is changing. So sometimes gamma we set we are having dynamically it is given, right? Similarly, processing architecture is also important. Centralized, every decision is being taken by the centralized. Sometimes it is distributive, right? Sometimes hybrid nature is there, like landslides networking, you can assume, right? There can be a small sensor, constant, unconstant, large sensors are there. So these are different attributes you need to take taken care. Now, important thing everybody is talking about, because when you are in a institute, people are asking what is your SCI index of paper. Normally SCI index people are talking about. So I have taken that term and I have redirected it. SCI mean for today's lecture is what you are going to sense. Another thing, what you are going to connect, what you are going to interact. See, sense means there can be different sensing parameter, right? Environmental different parameter, right? So vibration, lot of things are there. For structure, there can be acceleration, there can be concrete temperature, there can be displacement, there can be crack meter, there can be rain meter. So what exact, and also there can be pH, because I am maybe interested in corrosion. So what exactly quantity you are going to sense, right? Whether it is a single sensing, multi sensing. Now another thing is that how I am going to connect that, right? Whether it is a single platform, whether it is a distributive platform, and then finally where I am going to interact, right? Interact maybe a common person interaction with the mobile. So interface part, for example, if you will consider these three aspects only, the challenges you can understand. For example, interact we will consider where now you are going to interact with a blind person. Now you are aware of that blind person cannot see. So it means it can feel or it can listen. But you can see a person is a disabled, right? A person who is not having any action, he cannot move his hand. If he is driving a wheelchair, can it be controlled by some eye movement? Right? Now the important thing is coming up a BCI, where brain computing interface. People are interested in the cognitive load. They understand if a wheelchair person is thinking it is moving. There are of course noise will be there, but nowadays people are talking about the BCI, and BCI mostly they are going to have in a drone based application, where will be driven because of our thinking, right? Pilots think are there. Similarly, people who are using the Apple phone, they are aware of that. A series there where people are talking about means speaking interface is there. So this interface is going to give a different dimension, and sometimes you can have my system is having n number of interactions are there and number of interfaces are there, which makes your system with others. Similarly, it is a simple recording or it is a computing processing intelligence inbuilt, a complete system is there. So the important thing is to take care about your SCI index. SCI index here means about the technology. So smart autonomous sensor system is there. It will vary from application to application. For example, acceleration or tilt. If dam is there, there may be tilt we are interested. if people are walking, people may be in acceleration, people may be interested in earthquake, right? Machine vision, you are aware of that. They may be interested in finding the cracks, right? They may be interested in different kind of a samples over the moving belt, right? People may be interested to know the moving person, moving vehicle, position, presence, proximity, velocity, displacement, temperature, humidity, acoustic gases. A different kind of applications can be possible, and they are not limited with that kind of a sensors, but there can be more with the passage of time. So ultimately, what we are going to do, either we are predicting or we are doing the early warning. If we are saying prediction or early warning, it can relate to any of the thing. For example, real world sensor is coming at the first place, and that sensors can be agro related application, that sensor can be biomedical related application, that sensor can be geohazard related application, that sensor can be climate related application, environmental related application, strategic application, or intelligence structures are there. So what we are going to take the data, we are always getting the data, and data is targeted in nature. So what we are going, it can be X-ray, ultrasound, vibration, temperature, one channel, two channel, n channel, right? Low frequency, different kind of a data we are getting. And then what we are going to do, we are going to process the data. Process can be filtering point of view, process can be extracting the particular information, and then ultimately we are going to have a computational intelligence. It can be some knowledge base, it is taking care of the sample which is already been trained, whether it is looking for that or particularly thing it is matching with. So ultimately we are doing the knowledge representation and data mining. And with the prediction, what we are going to do, we are going to control either some plant, we are going to have a control of a different environmental condition. We are going to inspect whether there is some cracks are there in a building or not. Monitoring is there, we are going to monitor the process, whether temperature is about some threshold or not. If above threshold is there, suppose beverages plant is there, our beverages may be contaminated, so they need to take care. Then prediction are there, we are predicting that COVID behavior is there, this may be the possibility of that, on the basis of facts, on the basis of data, how we are going to take care of this. We are going to predict this time agriculture produce will be like this, and then we are forecasting the information, and we are going to recognize whether that particular thing is there. Similarly, diagnostic things are there. So what we are going to do, we are going to have a SIM4. This I have derived either control, inspecting, monitoring, predicting, forecasting, recognition, or diagnosis. So this is very important. Industry 4.0, where intelligent sensor and system is playing very important role. You can see, if you will see, there are certain wheels are there. One is the autonomous system. Autonomous means self-diagnosis, self-awareness, means because automatically it is taking care. Best optimized performance it is giving. And internet of services mean things are connected over the network, over the LAN, so that if anything is mishappening, automatically it will be informed. It is aware of that, what is the supply chain, what are the other integration problem are there. And internet of the things, they are connected, ability to connect and manage divide into the real time situation. And flexible manufacturing, 3D metal printer, machine to machine interface, right? And ultimately analytics and cognitive. It is predicting, self learning from the examples, from the whatever be the scenario it has gone through. So if we talk about industry, we found these are the 5 different wheels which is playing a very important role into that. So you see, this is very important aspect, because we are going from first generation to the second generation, third generation, and now we are talking about the fourth industrial revolution. The fourth industrial revolution, the important thing is a learning from the aspect where cyber physical system is there, where AI is playing very important role, and new generation integrative manufacturing we are talking about. So it is evolving. Initially it was human and physical system, then digital manufacturing was there, then digital networking was there. Now we are talking about new generation integrated manufacturing. So cyber physical system, where AI is very important thing, where things are evolutionary in nature. So it is learned because of the experience, because of the things. And the important thing in industrial simulation, system integration, security, cloud, additive manufacturing is very important. when a 3D metal printers are there, whatever we want to, a very complex drawing, and with the lightweighted we can do augmented reality, and big data is being generated because we are talking about a n number of sensors, right? So ultimately, industry V4, there is a industry information technology, there are sensor technology, there are modeling, there are automation, there are tools, and also the monitoring. It can be oil machinery, factory automation, smart sensor, data fusion. So all these things is going to give us a different dimension with the inbuilt intelligence. So this is an example I am talking about the industrial V4 where industry 4.0, where I talked about the additive manufacturing. Now you try to see these figures, right, or try to see this outcome of this. The very complex structure, light weighted but a very rugged. Now you can see titanium one reduction weight up to the fifth level, 5 level, 1/5 of the weight is being produced, but the strength and the different kind of a complexity of an engine is very high. And this kind of manufacturing, whether it is a bone related one, particularly bone can be customized according to the user. That is a human machine interface. And now one more application, because now I am thinking I should let you know, because you may be from the different fields. I am going to give you certain application with the sensor. Like people are talking about photonic nose for health, and these health can be a oral cancer, this health can be the lung cancer, this health can be kidney related problem. Three things are being taken care. Now they are nothing but a fiber beads are there, which you might have seen at your home when a lamp is there and a lot of lights are coming from the fiber beads. It is the same thing is there. So it is a bundle of beads. When you smell here or you breath, right, then there will be the order will be brought to the lowest level where camera is there, and we are going to record this order delivery is there. Once this order delivery will be there, then automatically there will be different kind of a change will be observed, and this change we will record, and this going to be have the different kind of a pattern recognition, and then vapor knowledge base will be maintained for different, and we are going to have a health diagnosis. Now you see the important aspect is this have a material coating. What kind of a coating is required so that your order, which is a fiber optic things are there, and it can be delivered to the bottom portion so that it can be acquired nicely. And another thing is that if it is acquired, then how it is converted into the signal. Once it is converted into a two-dimensional signal, then we are going to have a vapor knowledge base, which is already developed because of the known facts, where we know that this person is having this disease, how much depth we are having, how much variations we are having, how much regional variation, how much multispectral of things we have taken care. But this is going to be a revolutionary one. People are nowadays talking about this technology. Another thing is a snow depth sensor. Snow depth, I talked about, okay, nowadays China's conflict is there. Even nowadays, it's cold is going on. So snow will be accumulated. How we will come to know, okay, that how much snow is being accumulated till date, so that we will come to know, okay, we should send our soldiers or not. How it will work? You are aware of that. Velocity is equal to distance upon time, right? It is having a piezoelectric sensors are there, which is having 25 kilohertz to 40 kilohertz, and now a wave is being transmitted, and a piezoelectric transducer, they are a trans receiver, and after reflecting back, it is coming back. So what we are going to do, we are going to take care of the time. Velocity of sound is aware of us, and v is equal to distance upon time. So when there was no snow, we have calculated 1d1, and when snow will be there, we will calculate the d2. So d1 minus d2 is the snow depth actually. But it seems very easy, but it is not like that, because you are aware of that Vt is equal to V naught into 1 plus T by 273 under root. Means the velocity of sound is changing along with the temperature. And when snow is there, there can be minus 5 degree, minus 10 degree, minus 25 degree. So with the change in temperature, your velocity of sound will change. If velocity of sound will change, then it need to be compensated. How you are going to compensate? This mathematical calculation you need to do. How, if you are having a microcontroller, you are having microprocessor or these things, how continuously this kind of thing your system get overflow. So you need to maintain a lookup table. once lookup table, you should have a temperature sensor. See if this is the temperature, the value will be given by the lookup table. Then it will be easily implemented. So always try to see the solution of a problem. Otherwise, you will be nowhere, because you are going to solve the VT equation. Certain equations is being solved. So this is working on a piezoelectric crystals. And smart structures are there. This is very important. One of the important parameters nowadays, people are facing gas pipelines or oil pipeline. What people are doing, people start digging, and they are having the current system in 24 hours or 48 hours. They try to localize it. They are not able to detect whether there is a leakage, and in between that 24 hour, 48 hour, there will be lot of problem will be there, because oil will be taken out from the fields. So people do not have this technology, and people are demanding this technology, because a pipe of a 5 feet kind of a dia, and people are interested if fiber cable is there, if anything happen because of this JCB, because of intentional cut, how they will come to know there is a problem. So this is a very important challenge is there, where sensors and their technique, and also the classification, cloud computing important thing is there. Similarly, smart structure, where bridges, railway structures are there, railway bridges are there, right? Railway bridges are of a lot of problems are there, but we do not know what technology, how to do. Even bridges are there, buildings are there. So these are a very important thing need to be taken care. So what exactly we are monitoring for structural health monitoring? We are monitoring the acceleration, we are monitoring the strain, we are monitoring the environmental condition, like humidity, temperature, curvatures are there, displacement, load and tilt. So what we are going to identify, whether there is a corrosion in the building, in the steel bars, whether there is a crack, whether it is strengthened enough to handle, like Qutub Minar is there, our Taj Mahal is there, whether they are able to handle that kind of a crowd, what kind of tension, why it is being produced, location of delimitation. See, here we need to try to understand. Sometimes people can say it is a civil engineering aspect, but you see who is giving the sensors, who is giving the system, who is giving the application, yeah, who is designing the machine learning into it. So I am saying the sensor and system is a requirement of the all the field. So how we are going to design this mathematical model? Structure will be there. There will be a sensor array, and this sensor array will be combined to form certain kind of a Y, which is going to give us a damaged or undamaged situation. When undamaged will be there, then automatically very smooth kind of a pattern we will get from all these sensors. But if there will be damage, there can be spurious peaks will be get in a frequency spectrum. So by seeing this, we can easily identify. Now see, instead of structure, I will have a motor, like electrical machines are there. If there will be some problem, how I will come to know that that is damaged or not? Because it is not going to produce the desired amount of energy, and there will be leakage of energy will be there, and there may be an accident. How I will come to know it is damaged or undamaged? So these are the different kind of a mathematical model, and our mathematical model may be differ from the other mathematical model, right? Another thing is a artificial organoleptic system. Now this is a future, and according to the research, people are trend, people are saying another 10 to 15 years will be in this area. Where what we are going to do? We are having a taste buds. Our brain is there, our neurons are there, and say e-tongue, and we are talking about e-tongue, e-nose, right? This is the area where there is a lot of demand or convergence of technologies are required. So these taste bud needs to be converted into the sensor array. Here we are talking about the electrochemical in nature, because some kind of electrodes are there which is producing the different kind of, and it comes under the area of acquisition, where lot of sensors array are there. They can be placed at a different kind of a dimension. So what we are going to have, we are going to have a feature extraction, that is known as a data treatment, and it is also the same kind which we are going to find out in our brain. And then different kind of a pattern recognition or comparison will be there. Whatever be the information we are having, that we are having firing. Accordingly, we will have a taste, whether it is sweet, sour or bitter. Then we are having a classification based on training, so results are there. So you can see each of the aspect is giving us a challenge, and a lot of innovations is required in terms of a replicating the test buds, replicating the brain, replicating neurons, replicating the classification. So you can see what we are going to have. We are going to have a e-tongue, we are going to have e-nose. You can say adulteration in a water, wine, right? It can be milk. There are n number of things are there which where these applications are there. So what we are going to have, we are going to have odor receptors, lot of database are required. We are going to have a brain thing, neuron computing results are there, so that we can pinpoint that what kind of a smell it is, what kind of a things are there. So it can be applied to the n number of things, n number of applications. And another thing which nowadays is attracting, and this is a very good recent paper I have seen, this is a distributive comfort level indoor air quality monitoring system. Nowadays, people are also extending this with the COVID. If in-house some bacteria or some virus is coming along with the air, it will be detected and automatically refreshing or sanitization activation, deactivation required. So there is requirement of a lot of bio-inspired sensing device where airflow, motion, optical IR, and gases, of course. So these kinds of things are there, which required certain kind at the different office level, and very miniaturized level of thinking are required. And they are, although there is a lot of innovations are there, but still it is not at par, and people are only experimenting into this area. And another, this is very important thing, multi-sensing platform for pilot cognitive state. This pilot cognitive state is very important thing. When you know pilot is there, so what we are going to do, when it is under the training, there is a free fall. When a plane is free fall, when it is coming to the earth, then its g level is increasing. G is nothing but our gravitational force, and when gravitational force become 4 to 5 g, then there is a chances of a brain hemorrhage, and then we do not know whether pilot is going to have a brain hemorrhage or not. So there is a requirement that defense want some kind of a technology which should not be applied to the user body. One condition is that if anything we can apply to the uh, pilot, we can easily detect by having EMG signal and other signal. But the problem is that psychologically they do not want to put any sensor or anything on the body. So when it is a free fall, automatic by the acoustic, by the thermal imaging, that kind of a system is required. And you can see it's a very latest paper of May 2020 where they done certain kind of a simulation. Very latest trend thing is it is required. If it is free fall is there, it having a control in the ground which can brought to the normal level, so that before hemorrhage is there, it can be taken care. And another thing is this soldier psychological behavior is there. You know, sometimes thermal become problem, and you know how many sensors are there. Wearable sensor on the boots, there belts are there, right? Walkie talkies are there, or there can be other on the body, and number of sensors may be there. So power become important, data, human factors, watch can be there. If snow avalanche is there, we are able to find out. So thermal stresses are there, fitnesses are there. If some problem is there, how we will identify, and also n number of things we can communicate. So this is also a strategic thing where our people required intelligent wearable system with n number of sensor being customized and on the body. And another thing is the intelligent potato storage system. You are aware of that, potato or maybe onion or any vegetable which is of important nature. So after some time they get sprout, right? Or they may get sweet. So whether we can maintain a automatically AN based solution, so that a different kind of a carbon, oxygen, humidity, CO2 level, and these can be maintained automatically, so that it should not only taken care for a 2 month, 3 months, 3 years, 4 years together, a good quantity can be maintained. So intelligence, not only potato, but you are aware of that in Punjab region, lot of wheats are being wasted because of non-availability of the storage system. So a good storage system with the intelligent behavior is required at need of the hour. And also you can see the technology for sorting, grading, packaging of fruit. How we will come to know that these are the apples, these are of a good quantity, good quality. different kind of a camera will be installed. They will allow to move from one portion to the another portion. So in between, all the camera is taking one image and it is being processed to detect whether it is of a good quality and a bad quality. So accordingly, we can sort them according to our image processing method, and sometime maybe thermally we can take care, so that internal things we will take care. And smart parking load guidance system, this is very important. When we are going in a mall, we are going to here and there, and if you consider the oil consumption, for example, n number of vehicles in a year, so if like that space available, it will see a C block, no space is there, B block, this much space is there, a, or maybe the nearest one it will tell, so that it can be really good thing. For that you need to have a vision sensor, intelligent sensor, right? Also the recognition detection part, right? Once and adaptive also, when it is being taken care, it should be removed from the basket, right? So another area is that IoT based healthcare to wearable. Previously we are going to have a treatment of a patient, now we want our health. There is a paradigm shift, we want to enhance our health. Here we do not want to have a disease management, we want to have our health management. It's not a patient compliance, it's a health experience. It's not for the patient, but it's for the customer. So what we need a body sensor network. And when body sensor network, it should be dynamic, it should be continuous 24 into 7, it should be preventative, it should be early diagnostic, home based, post operative, right? Anytime, anywhere, anybody is there. Now you can see this picture, there are a lot of gadgets are there, lot of wires are there. If sometime people are having some attack or something, he may not be comfortable because he is not allowed to meet his near ones. Suppose instead of that, all these things, we will have a gadget, some jacket will be there, he is wearing, and all the things is being monitored. GPS is there, mobile is there. Once it is about some threshold, automatically nearby center will inform that a particular ID person who is at this location is having problem. Like that, it can be thought of. And this is very important, smart clothing and future of patient monitoring. You can see, I have seen this in Germany in 2009. You can see when we are driving a car, we are holding a steering, and steering is having a this material such that our skin impedance is there, which is going to tell us the health index. And this belt is there, it is also having the electrode, and a belt is having electrode and seat is having electrode. He is not aware of that, because when we are driving a car, we are sitting on and wearing a belt and holding a steering. We are not aware of that, whether our seat is fabric is monitoring, our belt is monitoring, and you can see the health index is there. If our BP or some pulse rate will be high, it automatically give alarm, right? Similarly, if we will put another sensor like drink kind of a thing, if person is a heavy drunk or feeling laziness or mode is there, then a alert can be generated. And this is a really a very futuristic things people are thinking in country, where this thing will be available shortly. Similarly, why I need to have a blood pressure at particular time. I'm on 24 into like Holter is there. So like that, our mobile will be there, health for everyone. Whether I'm sitting, the electrode will be on the chair, my textile will have to automatically health index will monitor, right? So it required a textile electrode, textile sensor are there. Similarly, intelligent health center. Here, if you will permit, I want to show you one video. Is this screen visible to you?
Yes, sir.
So this is our project actually, which we have done in the Chosala village. You can see this. This is a e-health center which we have designed there, and there people were not having any doctor. It's audible to you?
Your voice is audible, sir, but there is no audio from the video.
Okay. I don't know why it is not there. So it is saying a father is having dream, a family is dream to have a big things. That's why he rented a land and also purchased some seeds, so that he is going to buy a tractor. So that was the dream family was having. And day and night he was hard working in the field, so that before cloud came he should drop all these seeds. But in between he was having health problem. in a village where even no RMP was available. And in village, what kind of a treatment people are getting, even nowadays, when we are saying we are in the 21st century. So this boy has seen this e-health center, and then he's asked whether this can be possibility for his father or not. Then he tried his best, but he could not help, so that people are not talking about. So what we did, we have made, these kinds of containers are there. So if disasters are there, the container are having one is a path lab, another is having a complete OT, another one is a doctor where people can discuss together, and lot of digital sensors in belt. There will be any disaster, it can be airlift by the truck. You are aware of that in Uttarakhand. Uttarakhand, lot of problem was there. Everything has been damaged. This can be directly brought where people can work. This is the Chosala village near Kathal. A doctor is coming, they are having biometric attendance, and this ECG equipment all are digital in nature, and all are having cloud computing. So people are having telemedicine, they can talk together, interact together. A small village where no RMP was there, such kind of facility has been given under the NKN, National Knowledge Network, so that he has taken his father there. So this is the actual thing, how you can see the all things are digital in nature. All the health record, cloud is there. Even the stethoscope they are having, it is digital in nature. Every data is there, and lot of doctor can talk together. And they were you can a spirometer where lungs and all this data can be uploaded. The same thing which I had discussed with you, right? Every digital data has been taken. You can see all the data ECG even, right? So a different kind of data we have received, and a good publication we got from this kind of thing. And a good pattern also we have detected in that village. It is a model project which can be extended further. Now you can see even the ECG is simple stethoscope. It is recording is there, and all in a recorder, center recorder is there. And good quantity means I can say data has been generated so that a future next generation drugs and all these things, and it is helping to a farmer where he can take help. Now you see he again gone to the field, and the dreams are coming true. And the important thing I want to mention here, he is getting signal on mobile. That you see this signal IoT based. SMS has been received indicating that your next checkup is on this. This is actually implemented in a village, right? So I am saying with this kind of a technological revolution, we are going to really help a people persons, right? So this is a intelligent e-health center which we have implemented there and shown as a model project to the national knowledge network, okay, how the network can be used. And if there is no buildings, cracks are there, disasters are there, doctors will be available, but hospital will not be available, and it will take time. But this kind of thing can be airlift where our countries are having n number of things are there. Similarly, wearable technology for elderly care. This is a really becoming a great problem. You are aware of that. One lady was dead, and she was having only son in US, and neighbor got to know only after 15 or 16 days. They can have a fall detection, climbing detection. So sometimes people may forget to come back to the home. So whether we can have a boot or acceleration sensors, whether how to detect this activity, whether they are walking, bending, lying, this is again a challenge are there. And so there are different kind of a belt people are saying, sensors are there, accelerometers are there. So the important thing is automatically detecting from the signal that it is of a walking stage, falling stage, or in between, because this is a really great challenge when we are talking about offline and online in a real-time computation. And also sensor sensitivity problem will be there. Similarly, sometimes people are having this accelerometer sensor near the nose, so that from that signal is continuously being generated, so that they can find out whether there is an ideal seating, they are talking or they are walking. So lot of innovations are coming up in this area because this is need of the hour. And another area is the surveillance and security, which we were discussed when, for example, this is our campus, nobody is allowed to enter. And this we have designed, you can see this work, where there is a lot of geo sensors are there. And this is the intelligence system we have designed. This is our development only. And you can say when a person is moving, automatically it will be detected by the sensor. And this is real-time signal processing are there. It is going to activate the thermal imager, so that we can also find out whether the person is running or it is how with what speed where it is moving. So this is very good work is there using GPRS modem and geophones are there. And also you can see this work where person is moving with the UWB radar, ultra wideband 3.1 to 4.8 gigahertz sensor, and a person is moving whether it is crawling or behind the bush. So it is able to detect these kinds of a sensor, and these are giving really a promising result for detecting the person in a real time in different kind of a scenario. And important one more area nowadays, nature. In the nature I have seen in 2020, where people are having smart floor monitoring system, where these patterns they are having a different PET, PVC, polyvinyl and other chemical coated are there, so that there will be a signal acquisition, light controls are there. Also there can be a position center sensor, activity monitoring, individual recognition, also for the security whether an unwanted person has entered or not, right? This is having an further application in smart home, healthcare, security, AIoT. And you can see this is really a very important thing, how we are going to save a convolution neural network, deep neural network, so that you will able to identify whether which portion light need to be on, light need to be off, some sensor need to be activated, how we need to give grant access. Similarly, we need to find out whether a person is slow walking, normal walking. But here you will see the important challenge is there. Okay, sometimes foot is there, whether 20% is there or 80% press is there, sometimes 60%, 40%. So different kind of a combination. This is a really good article came in nature.com, and really they have identified slow walking, normal walking, fast walking, running and jumping from the signal processing point of view, because they were having the pressure sensor, they are having the accelerometer at the floor level only. And this is the last work I want to tell. This is the earthquake warning system we have designed for Delhi Metro. So because time is also passing, so this is the earthquake warning system. What it is doing before reaching earthquake, it is giving the alert to the Delhi Metro. And this work, how it is working, whomsoever visited Delhi, Mundka is there, Metro Bhavan is there, Botanical Garden, Faridabad and Hooda City. If earthquake is coming from any of the direction, it is being recorded, and it is generating the warning in a real time to the user, to the registered user. And because of that, in 2016, 10th April, approximate 19 second of pre-warning when the disaster wave not been sensed at the Chandigarh, but the system has alerted that earthquake is coming in a real-time mode. And this system where there is a real-time network, all the protocol, all the communication, all the signal processing, all the sensor work together, third time in the world, where Mexico and Japan has demonstrated this technology, and we have demonstrated this technology in a real-time mode, where the hive network of the sensor has generated a signal in a real-time mode, and real-time processing, intelligence, everything has been done at the different level, and then generated a alarm signal for that, which has resulted as a very good awards and recognition, which Madam has mentioned at the initial level. So this is the theory only, and the practice you can see the theory whatever is there, it seems to be greenfield, but in actual real practice you can see this is the. There are a lot of technological challenges are there, and thanks a lot for this. Now I am welcome for any question which you want to ask me.
Thank you so much, sir. You have shown all the real applications of sensors, different
I
sensors,
I tried my
intelligent.
best.
Yes, sir. It was really nice and informative. And now the session is open for questions from the participants.
Yes, sir. Good afternoon, sir.
Good afternoon.
Sir, firstly, I would like to thank you. This was a very informative session.
Thank you.
Yes, sir. Sir, the slide you showed for the e-health centers, I would like to ask, sir, how one can approach to the e-health centers. Suppose, as you showed in your video, that from a village, some persons he is having a disease, so the student he called the e-health center. Like I wanted to ask that how we can approach the e-health center.
See, e-health center nowadays there are three e-health center in the country which we have demonstrated. One is a Chosala, right? For example, if you want to know anything, you can personally visit there, and you can contact. Even I can get one person in IGIB, Dr. Viren Sardana. You can contact him. Currently, he is taking care, right? And
Okay, sir.
because it's not e-health center, means I'm not talking about people might have talked about e-health center of Punjab also. This is a e-health center where each IT, effective, affordable content health using the IT. It was the project, right? That is why we
Okay,
have given e-health, where content-based health has been provided through the use of information technology, right?
okay, okay,
Nowadays
sir.
there may be other e-health center. If you want to approach that, you have to go to Dr. Viren Sardana, IGIB, Delhi.
Okay, okay. Sir, like these e-health centers, like you showed that they themselves go to the village wherever if there is some requirement, right?
Actually, sometimes there are politically based also, who is giving land, who is providing the infrastructure support, right? So
Okay,
some MP may come forward and they can say, okay, land I will give, I will provide you all the support, right?
okay, okay,
Because this is a research level kind of a project which is demonstrated at one particular place, right?
okay,
Then it can be
okay, sir.
extended to other.
Okay, sir. Sir, one thing more I would like to ask that like these e-health center, are these are also helpful in this pandemic, like for the
See, whichever health center are there, they are helpful, because for example, even if we are feeling fever or sometime nauseatic or something, sore throat problem is there, we are thinking covids are there, so they can visit and they can diagnose themselves. That can be also a detection center can be there, right? Primary detection can be there, so that they can refer, or they will be more authentic rather people are afraid of, or some private kind of a problem may be there. So these government can set up these kinds of a center as well.
yes, sir. Like this, sir. Nowadays, like the people from the villages, they are unwilling to come to the
Not even
like.
villages, and even the
Uh,
main
yes,
cities,
sir.
metro
Main
cities
cities
also.
also. Yes, sir.
It is of
So
the
that,
same thing. Rather,
that's
they
why,
are
sir.
less
I
worried.
was
I can say villagers are less worried as compared to metros people.
yes, sir. So that's why I was asking that if the e-health centers they are so much helpful, like they are having the all the facilities and they are also connected to the cloud. So if they can if they can go to the village themselves and collect the data from the people and like people they don't have to move to the longer distances, and also it will be secure for them also. So it can be a better option. So in this pandemic, right? So we can detect more of the cases, either they are positive or the area is infected or not.
Yes, definitely, because see, this is a initiative and it is an example also. Sometimes no need to have a building or these kind of a thing.
Yes,
These
yes,
are
sir.
not only extended to the lab level, right? Research level, validation level. It can be a server we can extend, right?
Okay.
Even school also, some kind of a lab, small dispensary can be extended to a particular village.
Yes, sir.
There are
Okay.
n number of things can be utilized. Even the person who is not having for example, home, they do not have any shelter, right? It can
Yes,
be
sir.
taken care. Even for the soldiers also, by having some insulating thing, it can be extended.
Okay. Okay. Thank you, sir. Thank you, sir.
Any other questions from the participants? So basically, CSIR labs they are more concentrating on the development of real-time sensors. So they are bringing the product sensor as a products for real-time applications. So they are implementing it. So most of you are the research scholars. So you can get the suggestions from sir, for what are the future trends and the research aspects?
See, actually, I told you
Okay,
कि
ma'am.
in some book, in some slide I have mentioned, there are
Yes.
different type of layers are there. I
Yeah.
told that there can be lot of variations. For example, people are talking about multiplexed ADCs. Like you can have an independent multi-rate system. When you will have multi-rate system, you can acquire a different quantity. When quantity will be there, then also you can have an intelligence layer into how you are going to process the thing.
Hmm.
Another thing is that minimum number of, for example, you are acquiring 20 parameters and also different kind of a feature. What parameter is very important? Whether you are interested in accuracy, fast. Sometimes people can say I can afford 80% of accuracy, but earliest. Sometimes person can say ki I need 100% of accuracy, maybe delayed. So all things are depend upon what is our ultimate requirement. And sometimes we are estimating the things when we are talking about early warning, right, alert system, then we are estimating so many things.
Yes. Yes, sir. Any other questions? Okay. I think there is no questions. So thank you so much, sir. Thank you for sharing your valuable time,
Thank you,
and
madam.
it was highly informative. Thank you, sir. Thank you
Thank
for
you.
joining
Thank
us.
you.
Thank you.
Thank you, madam.
Madam, will you share all the informations to us?
Yes, ma'am. We will share the YouTube link. So there you can find all the videos of all the sessions.
And the contact mail IDs also we require, madam.
Yes, ma'am. It will be in the. I think it will be in the slide. So if it is not there, we will provide you.
Okay, ma'am. Thank you. All the sessions were nice, ma'am.
Thank you. Thank you, ma'am.